get ready to have your mind blown, because something is about to happen that will rewrite the history books. On October 29, 2025, we're about to witness a cosmic event that's never been documented in human history. 3 Atlas III confirmed. Visitor from beyond our solar system will make its closest approach to the Sun while playing the ultimate game of cosmic hide-and-seek. Completely hidden from Earth's view for 3 critical weeks. And here's the kicker. NASA knows something they're not telling us about why this timing matters. Let me be crystal clear right from the jump. This isn't some wild conspiracy theory or baseless speculation. We're talking cold, hard facts backed by orbital mechanics and spectroscopic data. We're talking about a specific moment in time, October 29th, when the most chemically bizarre object ever detected will reach its closest point to the Sun at the exact moment we can't see a damn thing. Here's what the mainstream media isn't covering, what almost nobody outside the tight-knit astronomical community is whispering about. 3 Atlas has been pumping out nickel tetracarbonyl, a compound that's never been spotted in nature, only in industrial manufacturing. The Very Large Telescope confirmed it, 4 grams per second with 0 iron present. Something that shatters every established model of cometary chemistry we've painstakingly built over decades. And then there's the trajectory, a 0.2% probability of aligning this perfectly with Earth's orbital plane by pure chance. Close encounters with Venus, Mars, and Jupiter that NASA's own calculations show have a cumulative probability of just 0.05%. These aren't just numbers. They're screaming red flags that something extraordinary is happening. If you're here because you want the unvarnished truth about what the data actually shows, not the sanitized official statements, then you're in the right place. Hit that like button, subscribe if you haven't already, and drop a comment telling me whether you think this perihelion timing is just cosmic coincidence or something more. Because when Harvard physicist Avi Loeb, the same scientist who challenged the consensus on Oumuamua, assigns a 30 to 40% probability that this object doesn't have a fully natural origin based on 7 distinct anomalies. We're not talking fringe theories anymore. We're talking about compound statistical improbabilities that make your head spin. We're talking about a sunward-pointing jet that defies everything we know about comet physics. We're talking about nickel, emissions matching industrial alloy profiles. We're talking about a 3-week blackout period that begins in just 48 hours. And by December 15th, when 3 Atlas makes its closest approach to Earth at 170 million miles, we'll know whether those hushed conversations in astronomy departments around the world were justified. Let's dive deep into what happens during those 3 hidden weeks behind the Sun. Chapter 1. The object that shouldn't be this massive. In late September 2025, a paper appeared on the Arxiev preprint server with an unassuming title, Astrometric and Photometric Analysis of Interstellar Object 3, I-Atlas. But buried in that technical analysis was a number that fundamentally changed everything about this object: 33 billion tons. That's the minimum mass of 3 Atlas. Calculated not from direct measurement. We can't exactly weigh objects in space, but from the absence of something we should be seeing. Non-gravitational acceleration when comets get cozy with the Sun. ice on their surface sublimates, turning directly from solid to gas. That gas jets off into space, acting like a tiny rocket engine that pushes the comet, changing its trajectory. In measurable ways, astronomers call this non-gravitational acceleration, and it's one of the defining characteristics of active comets. We can detect it by tracking a comet's position over time and comparing where it is to where pure gravity says it should be. If it's ahead of schedule, behind schedule, or off to the side, that tells us outgassing is pushing it around. But 3 Atlas, it shows almost none of this. Its trajectory matches a purely gravitational path within extraordinarily tight margins. The upper limit on its non-gravitational acceleration is less than 15 meters per day squared. For an object actively releasing gas, and we know it is because multiple telescopes have measured the outflow, this is vanishingly small. The only explanation consistent with the observations, the object is so massive that the thrust from outgassing doesn't move it measurably, like trying to push an aircraft carrier with a garden hose. The force exists, but the mass is too large for the acceleration to be detectable. So they did the math. Given the observed gas loss rate of approximately 150 kilograms per second, measured by the James Webb Space Telescope on August 6th, and given the absence of detectable non-gravitational acceleration, what's the minimum mass this object could have? 33 billion tons. And if you assume it's made of rock and ice with a density similar to other comets, somewhere between 0.5 and 0.9 grams per cubic centimeter, you can calculate a minimum diameter. The answer comes out to more than 5 kilometers, possibly significantly more depending on internal structure and composition. For context, the 2 previous confirmed interstellar objects, Oumuamua, discovered in 2017, and Borisov, discovered in 2019, were both small. Oumuamua was perhaps 200 meters across at its widest. Borisov was probably less than a kilometer in diameter. Both were modest chunks of material, exactly what you'd expect for debris ejected from distant planetary systems during their formation. 3 Atlas is 3 to 5 orders of magnitude more massive than either of them, a factor of 1,000 to 100,000 times heavier. This creates a statistical problem that's difficult to resolve through natural explanations alone. Objects in space follow a power law distribution. For every large object, there are exponentially more smaller ones. If there's one rock 10 kilometers across, wandering through interstellar space, there should be hundreds of 1-kilometer rocks, thousands of 100-meter rocks, millions of 10-meter rocks. The numbers explode as you go smaller. This pattern appears everywhere in nature. It's how crater sizes distribute on the moon. It's how earthquake magnitudes arrange themselves. It's how asteroid populations in our own solar system are structured. Big things are rare. Small things are common. The universe doesn't manufacture as many mountains as it makes pebbles. Based on planet formation models and estimates of how much rocky material gets ejected from star systems during planetary development, astronomers can calculate roughly how often we should expect interstellar objects of various sizes to pass through our solar system. For something in the 5 to 10 kilometer range, the expected rate is approximately once per 1,000 years, perhaps once per several thousand years, depending on assumptions about the density of interstellar material and the efficiency of planetary formation processes. We've been systematically searching for interstellar objects for roughly a decade. 1 decade of looking, and we found one of the rarest size classes possible. Avi Loeb has described this as the mass budget problem. There simply isn't enough rocky debris floating around in interstellar space, at least according to our current models, for us to be finding massive objects this quickly. Unless either our models are fundamentally wrong, or this particular object represents something other than random ejected planetary material. But there's another interpretation of that 33 billion ton number, one that requires thinking about mass in terms of structure rather than bulk material. If you were designing a vehicle capable of traveling between star systems over millions of years, you wouldn't build it as a solid chunk of rock. That would be impossibly heavy, requiring enormous energy to accelerate and decelerate. You'd build a shell, a thin structural framework with vast empty interior volume. That's how every long-distance vehicle humanity has ever constructed works. From ships to aircraft to spacecraft, strength through geometry, not through bulk, a hollow sphere. 10 kilometers in diameter with walls a few hundred meters thick could easily weigh 33 billion ton. It would have enough mass to resist perturbations from surface outgassing, especially if that outgassing were coming from ice and dust, coating the exterior rather than from the internal structure itself. And from our telescopes, it would look exactly like a solid comet. It would reflect sunlight appropriately. It would develop a coma as surface ESAs sublimate. It would display all the visual characteristics we associate with natural objects. This isn't proof of artificial construction. There's no direct evidence that 3 Atlas is hollow. We can't see inside it. We can only measure its mass through gravitational dynamics and infer structure from those measurements. But the mass creates a constraint, and that constraint opens possibilities that natural formation models struggle to accommodate without invoking extraordinarily unlikely coincidences. Chapter 2. The trajectory that threads through planets. Our solar system is relatively flat. 8 planets orbiting the Sun in roughly the same plane, like dinner plates stacked at slightly different heights. This plane, called the ecliptic, is a fundamental organizing principle of our local cosmic neighborhood, a geometric memory of the rotating disk of gas and dust from wood, which everything formed 4.5 billion years ago. Interstellar objects shouldn't care about our ecliptic plane. They come from other star systems with their own geometries, their own rotational orientations. When something arrives from outside, it should come from a random direction at a random angle. The probability that an interstellar visitor would happen to align closely with our ecliptic plane is small. Not impossible, but small. Approximately 1 in 500.3 Atlas arrived with an orbital inclination of 175, which means it's moving retrograde opposite to the planet's direction, but tilted only 5 from the ecliptic plane itself. Nearly flat, nearly aligned. That's the first statistical improbability. But the trajectory analysis doesn't stop there. 3 Atlas doesn't just pass through our solar system at some arbitrary distance from the planets. Its path brings it remarkably close to 3 of them: Venus, Mars, and Jupiter, and not just closed in space, but closed in time, arriving at each planet's orbital path when that planet happens to be nearby. Consider what that requires. Mars takes 687 days to complete one orbit around the Sun. Venus takes 225 days. Jupiter takes 12 years. They're all at different distances, moving at different speeds, and they're only in specific locations at specific moments. For an interstellar object to pass near all three during a single flyby, the timing has to align across multiple independent orbital periods. Avi Loeb and his colleagues calculated the combined probability approximately 1 in 20,000. On October 3rd, 2025, 3 Atlas passed within 0.19 astronomical units of Mars, roughly 18 million miles. That's close enough that NASA attempted to image it with the high RIC camera aboard the Mars Reconnaissance Orbiter, an instrument designed to photograph the Martian surface at resolution fine enough to distinguish individual boulders. Those images officially showed a diffuse coma with a faint nucleus, exactly what you'd expect from a distant comet. Nothing obviously anomalous, nothing that would make headlines, but the minimum orbit intersection distance, the closest 3 Atlas's trajectory, gets to Mars's entire orbital path is only 2.7 million kilometers. If the object's arrival had been shifted by just a few days, if its path had been tilted by just a few degrees, it could have passed significantly closer. It could have intercepted Mars' orbit at a point where Mars itself was present. After Mars, the trajectory carries 3 Atlas past Venus at 0.65 astronomical units on November 3rd, about 60 million miles. Then past Earth at 1.8 astronomical units on December 15th, the closest approach to our planet. Finally, it will pass within 0.36 astronomical units of Jupiter on March 16th, 2026, roughly 33 million miles. 3 inner planets, each approached during a single pass through the solar system. Each encountered when the timing places them reasonably near the intersection point. Any trajectory through the solar system will pass various distances from various planets. That's geometry. But the clustering of these relatively close approaches, combined with the ecliptic alignment, produces a compound probability that becomes increasingly difficult to attribute to pure chance. Loeb has used a gambling analogy. If you walk into a casino and watch someone roll double sixes 10 times in a row, you don't immediately conclude the dice are loaded. The odds are about 1 in 60 million, but it's theoretically possible through random chance alone. Nevertheless, if you witnessed it, you would probably examine the dice more carefully. You would consider the possibility that something might be influencing the outcome. The trajectory of 3 Atlas is that sequence of double sixes. Each element individually might be explicable as chance. Collectively, they create a pattern that warrants closer examination, but the most statistically provocative element of the trajectory isn't the planetary approaches, it's the timing of Perihelion. Chapter 3, The Hidden Window. October 29, 2025, at approximately 11:44 Universal Time. 3 Atlas reached its closest point to the Sun, 1.36 astronomical units, just inside Mars' orbit, about 126 million miles from our star. For a natural comet, this is the moment of maximum activity. Solar radiation at that distance should trigger intense sublimation of surface ices. We expect dramatic outgassing, possibly fragmentation events, significant brightening as fresh material becomes exposed. It's when comets reveal what they're made of under maximum thermal stress. On that day, Earth was positioned on the exact opposite side of the Sun. 3 Atlas was in solar conjunction directly behind our star. From our vantage point, every ground-based telescope on our planet was rendered useless by solar glare. Even space-based telescopes, not affected by daylight, struggled to observe because the Sun's corona and brightness overwhelm anything in close angular proximity. For 3 weeks from mid-October through early November, this interstellar visitor was effectively invisible to terrestrial observation during what should have been its most revealing phase. The probability of this timing arriving at perihelion precisely when Earth is on the opposite side of the Sun depends on how you calculate it. If you take 3 Atlas's trajectory and randomly vary its speed slightly, shifting its arrival time by a few weeks in either direction, the odds that Earth would be positioned for solar conjunction at that exact moment range from about 1 in 20 to 1 in 30, depending on the specifics of the orbital geometry. Not impossibly unlikely, but adding another improbability to an already improbable stack. Loeb has described this as a hidden vantage point. If you were designing a trajectory that allowed course corrections to be made without observation, you couldn't choose a better moment. Perihelion is the optimal location for what's called a reverse Oberth maneuver, using the Sun's gravity to amplify the effect of propulsive thrust while moving at maximal velocity near a massive body. In normal operations, spacecraft use the Oberth effect to gain speed. You fire engines when you're moving fastest, when you're closest to a gravitational well, because that's when a given amount of thrust produces the largest change in orbital energy. The same principle works in reverse. Fire engines to slow down at perihelion. The Sun's gravity helps capture you into a bound orbit, rather than allowing you to escape back into interstellar space. If 3 Atlas made such a maneuver on October 29th, we wouldn't have seen it happen. We would only discover the trajectory change weeks later when the object re-emerged from behind the Sun and we recalculated its orbital parameters. As of mid-November, when 3 Atlas became visible again from Earth, preliminary observations suggested its trajectory remained hyperbolic, still on an escape path from the solar system. No obvious signs of orbital capture, no clear evidence of propulsive maneuvering, but the data is still being analyzed. Precise orbital determination requires months of observations from multiple vantage points. Small course corrections made at perihelion might not become apparent until we have sufficient baseline measurements to detect subtle deviations from purely gravitational motion. The European Space Agency's JUICE spacecraft, currently en route to Jupiter but still relatively close to the Sun, observed 3 Atlas throughout November using multiple instruments. Those observations won't be fully analyzed until early 2026 due to data transmission delays and processing time if there were anomalies. If the object displayed behavior inconsistent with natural cometary activity, we won't know for certain until those results are published, which means we're currently in a state of observational limbo. We have enough data to confirm 3 Atlas survived perihelion intact. We don't yet have enough data to completely rule out subtle course corrections during the period when it was hidden from Earth's view. That uncertainty, that gap between what we can see and what might have happened is where speculation naturally grows and where careful scientists must distinguish between legitimate questions and unfounded assumptions. Chapter 4. What Hubble Saw. On July 21st, 2025, the Hubble Space Telescope captured the first high-resolution images of 3 Atlas, revealing details invisible to ground-based telescopes. The observations showed a teardrop-shaped cocoon of dust surrounding the nucleus, with a faint extension trailing away from the Sun, the expected configuration for an active comet, responding to solar radiation pressure. But there was another feature that drew immediate attention. A slight extension of scattered light, pointing toward the Sun rather than away from it, forward-facing, where cometary tails shouldn't be. NASA scientists quickly explained this as an imaging artifact. When you're photographing an object moving at tens of kilometers per second from millions of miles away, exposure time matters. The comet moves during the exposure, creating motion blur, and if that motion happens to be directed toward the Sun, as it was, since 3 Atlas was approaching perihelion, you can get apparent extensions in the direction of motion. Even though they're not physical structures, most astronomers accepted this explanation. Motion blur is a well-understood phenomenon in astronomical imaging. You track either the object or the background stars during long exposures, and whichever you're not tracking will streak. Nothing anomalous about it. But by late August, something interesting happened. The Gemini South Telescope in Chile captured new images showing 3 Atlas with a clear, unambiguous tail streaming away from the Sun, exactly where cometary theory predicts. The object had developed normal cometary features consistent with increasing solar heating as it approached perihelion. The scientists who analyzed those images declared it confirmation. 3 Atlases behaving exactly like a natural comet should. Case essentially closed, except the timing raises a question. For the first 6 weeks after discovery, 3 Atlas displayed ambiguous visual features, unusual brightness for its distance, unclear tail structure, that puzzling forward extension. Then right around the time it crossed inside Mars's orbit and solar heating intensified, it began looking more conventional. Loeb has suggested carefully, with appropriate scientific hedging, that surface appearance alone might not tell us about internal structure. A technological object traveling through interstellar space for millions of years would accumulate debris, cosmic dust, ice particles, volatile compounds. All of it would stick to the surface, freeze, build up layers. By the time it arrived in another star system, it would be coated with material that would respond to solar heating exactly like a natural comet surface would. Frost on the windshield, as he's described it. This isn't evidence of artificial construction. It's a reminder that we can't definitively determine internal structure from surface observation alone. A natural comet and a technological object coated in cometary material might be visually indistinguishable until you could examine them with instruments capable of penetrating beyond the surface, which we cannot currently do. We don't have radar powerful enough to probe 3 Atlas from Earth's distance. We don't have spacecraft in position to conduct close flybys with ground-penetrating instruments. All we have are telescopic observations of surface features and spectroscopic measurements of outgassing material. From those observations, we know the object is predominantly releasing carbon dioxide. Unusual, but not unprecedented. We know it contains water, ice, carbon monoxide, carbonyl sulfide, cyanide, and atomic nickel, all compounds found in various solar system comets. We know its surface appears reddish, suggesting organic material similar to what's found on primitive asteroids. Everything we can measure is consistent with a natural object. But consistent with natural is not the same as definitely natural. It means the observations don't rule out natural formation. They also don't conclusively prove it, especially given the statistical anomalies surrounding the trajectory and mass. Chapter 5. The chemistry that doesn't quite fit. In late August, the Very Large Telescope in Chile detected something unusual. In the spectrum of light coming from 3 Atlas, atomic nickel vapor released at a rate of approximately 4.6 grams per second as the comet approached the Sun. Nickel emission from comets isn't unprecedented. Several solar system comets have shown it, and it was famously detected in the Interstellar comet to Borisov. Planetary scientists believe it comes from the sublimation of metal-bearing minerals or the breakdown of organometallic compounds on the comet's surface. What was unusual about 3 Atlas was the apparent absence of iron. In nearly every documented comet, nickel and iron appear together in roughly equal proportions. This isn't surprising. Nickel and iron form together in supernova explosions, travel together through interstellar space, and appear together in primitive solar system materials. Finding one without the other is like finding smoke without heat. Not impossible, but suggesting unusual circumstances. Several explanations exist for this discrepancy. Perhaps iron is present but not being detected due to the specific conditions in the coma: temperature, density, radiation, environment. Perhaps the iron is locked in compounds that don't break down as easily as the nickel-bearing materials. Perhaps observational limitations prevented detection at the sensitivity required. Or perhaps 3 Atlas formed in an environment with unusual metal ratios compared to typical solar system chemistry. Then there's the carbon dioxide dominance. Observations by the James Webb Space Telescope showed that 3 Atlas is releasing carbon dioxide at a rate roughly 8 times higher than water, an unusually high ratio compared to most solar system comets, which tend to be dominated by water ice. This could indicate formation in an extremely cold region of its parent star system, far from the star where carbon dioxide ice is more stable than water ice over billions of years. It could suggest the object is genuinely ancient, older than our solar system, formed when the galaxy's chemical composition was different, or it could represent a surface coating acquired during the object's journey through interstellar space. Layers of carbon dioxide frost condensed from gas clouds it passed through. Each chemical peculiarity has plausible, natural explanations. None individually requires invoking artificial construction, but collectively they paint a picture of an object whose composition doesn't quite match the typical profiles we've established from studying thousands of comets and asteroids in our own solar system. The phrase scientists use is carbon chain depleted. 3 Atlas shows unusually low levels of the 2 carbon and 3 carbon molecules that typically produce the green fluorescence, often seen in comets. Yet, in early September, during a total lunar eclipse, when sky conditions were exceptionally dark Astrophotographers captured images showing 3 atlas glowing distinctly green. Where did the green come from if the expected carbon chains were depleted? Possibly from cyanide, which the Very Large Telescope detected in increasing concentrations. Possibly from buried material finally being exposed as surface layers sublimate away. Possibly from chemical processes we don't fully understand occurring. Under the specific conditions this object experienced, each anomaly resolves individually, but the pattern mass higher than expected, trajectory aligned improbably, chemistry slightly off from standard profiles. Visual features developing in unexpected sequence creates what Loeb describes as a persistent strangeness that warrants continued scrutiny. Even as most scientists reasonably conclude the object is natural. Chapter 6. December's closest approach. By December 15th, 2025, Atlas will have traveled approximately 400 million kilometers since its perihelion passage, following a hyperbolic trajectory that carries it past Earth at its closest point. At 1.8 astronomical units, about 170 million miles, it won't come particularly near our planet by solar system standards. Mars at opposition can be 15 times closer. Venus during inferior conjunction is 10 times nearer. Even asteroids that pose no threat routinely pass within a few million miles. But for an interstellar object confirmed to have originated beyond our solar system, this represents the closest documented approach to Earth in human history. Closer than Oumuamua, which passed at 0.16 astronomical units but wasn't discovered until it was already leaving. Closer than 2I Borisov, which never came within 2 astronomical units of our planet. The timing provides Earth's major observatories their best opportunity to study this object in detail before it continues its journey back into interstellar space. NASA's Hubble Space Telescope, the James Webb Space Telescope, ground-based facilities with adaptive optics, all will be directed toward 3 Atlas, capturing data across multiple wavelengths to characterize its composition, structure, rotation, and activity level. These observations matter because they represent our last chance to answer fundamental questions before the object becomes too faint to study. Is the nucleus solid or fractured? Is the outgassing symmetric or focused in jets? Does the rotation appear stable or chaotic? Do any surface features suggest internal structure? Most importantly, does the trajectory after perihelion match purely gravitational predictions, or do we see evidence, of course, corrections that can't be explained by asymmetric outgassing alone? The data analysis will take months. Precise orbital determination requires observations from multiple vantage points across extended timescales. Small deviations from expected paths become apparent only when you have enough measurements to establish a baseline and detect departures from it. Which means even after December's closest approach, even after every major telescope has captured its best images, we still won't have definitive answers about what this object is, or whether it represents something more than natural interstellar debris. Will have data, spectra, images, measurements of brightness, color, gas production rates, dust-to-gas ratios. We'll have refined estimates of mass, size, composition, and rotation period. We'll have trajectory information accurate to within meters per second. What we won't have, what we can never have from telescopic observations alone, is certainty about internal structure. We can't see inside objects from millions of miles away. We can only measure surface properties and infer what might lie beneath. This is the fundamental limitation of astronomy. We study the universe from a distance, using light as our primary tool, and light tells us about surfaces, about emissions, about reflected radiation. It doesn't penetrate. It doesn't reveal hidden chambers or engineered frameworks or anything. Concealed beneath exterior layers, so when December arrives, when 3 Atlas makes its closest pass to Earth and every major telescope gathers the best data our current technology allows, we'll be in essentially the same epistemological position we've been in since July. We'll know what this object looks like from outside. We won't know for certain what it is. Chapter 7. The questions science rarely permits. Throughout modern scientific history, certain questions have been implicitly discouraged, not through official policy or institutional censorship, but through subtler mechanisms: professional reputation, peer pressure, the risk of being dismissed as unserious. One such question: could any of the objects we observe in our solar system be of technological origin? The response from mainstream astronomy has been consistently dismissive. SETI, the search for extraterrestrial intelligence, carefully listens for radio signals from distant stars using methodologies designed to separate potential artificial transmissions from natural cosmic noise. This is considered legitimate science, funded by institutions, published in peer-reviewed journals, but suggests that a physical object passing through our solar system might deserve investigation as potentially technological, and the reaction shifts dramatically. The same scientists who carefully analyze radio telescope data looking for patterns that shouldn't exist naturally become hostile to the idea that we might visually observe something that shouldn't exist naturally. This double standard has a logical basis. The universe is full of natural objects: rocks, ice, dust, gas. The cosmos manufactures these in endless variety. The probability that any specific object we observe is artificial rather than natural is vanishingly small. Science operates on Occam's razor. Simpler explanations are generally correct. The simplest explanation for an interstellar comet is that it's a comet. But probability works differently when you're dealing with small samples. If we observed 10,000 interstellar objects and one showed unusual characteristics, dismissing it as natural would be reasonable. But we've observed 3. And the third one displays a cluster of properties that individually seem unlikely and collectively produce compound improbability, Loeb's approach, controversial within astronomy, is to propose a methodology for evaluating interstellar objects on a scale from 0 definite natural to 10 definite natural to 10 definite natural to, with intermediate values representing varying degrees of anomalousness. He suggests that any object rating above 5 should trigger coordinated international observation campaigns, rather than casual dismissal. By his assessment, 3 Atlas rates somewhere between 5 and 6. Not because there's direct evidence of artificiality, but because the aggregation of statistical improbabilities, trajectory alignment, mass anomaly, timing coincidences, chemical peculiarities places it in a category where thoroughness becomes scientifically prudent. Regardless of ultimate conclusions, most astronomers disagree with this framework. They argue that assigning numerical values to ambiguous observations creates false precision. They're proposing artificial origins for objects with natural explanations damages scientific credibility, that even raising such possibilities encourages conspiracy thinking among the public. These objections carry weight. Scientific credibility matters. Public trust in institutions depends partly on scientists not crying wolf over every unusual observation. The history of astronomy contains numerous examples of phenomena initially considered anomalous that later received straightforward natural explanations. Pulsars, initially termed LGM's little green men by their discoverers, turned out to be rotating neutron stars. Vast radio bursts, once mysterious, are now understood as emissions from magnetars. The face on Mars revealed itself as a mesa when higher resolution images eliminated the lighting effects that created the illusion of features. Pattern recognition is a survival mechanism hardwired into human cognition. We see faces in clouds, hear voices in static, detect conspiracies in coincidences. This tendency serves us well in evolutionary contexts, but produces false positives when applied to astronomical observations, where statistical flukes occur regularly across vast sample sizes. Yet there's a counter-argument, one that Loeb has articulated repeatedly and that deserves consideration even from those who ultimately reject his conclusions about specific objects. Science advances not by assuming answers, but by investigating questions. The scientific method doesn't begin with certainty about what will be found. It begins with curiosity about what might be discovered through systematic observation. The question, could this be artificial, is not inherently unscientific. It becomes unscientific only when asked without proper methodology, without falsifiable predictions, without willingness to accept contrary evidence. But if approached systematically, defining observable characteristics that would distinguish artificial from natural objects, gathering data sufficient to test those predictions, accepting the results regardless of preconceptions, the question fits within scientific inquiry's proper scope. What makes 3 Atlas particularly significant in this context isn't any single observation suggesting artificiality. It's the reality that we're now entering an era where interstellar visitors will become routine observations rather than rare events. The Vera C. Rubin Observatory, fully operational as of 2025, surveys the entire visible sky every few nights. Its discovery rate for asteroids, comets, and transient phenomena exceeds all previous surveys combined within the next decade. We'll likely detect dozens of interstellar objects passing through our solar system, perhaps hundreds. Each one represents material ejected from distant planetary systems during formation processes we've never directly observed. Each one carries information about stellar environments completely different from our own. And statistically, if technological civilizations exist anywhere in our galaxy at frequencies even moderately higher than Earth's uniqueness would suggest, some fraction of those visitors won't be natural. Not most, perhaps not many, but some. Finite percentage greater than 0. The question isn't whether we should investigate every unusual object as potentially artificial. The question is how to investigate systematically enough that we won't miss the genuinely technological ones when they arrive, while simultaneously not wasting resources pursuing natural objects whose properties merely seem strange because we lack sufficient data. Loeb's proposed scale represents one attempt to formalize this process. Others have suggested different frameworks. None have achieved consensus, partly because the astronomical community remains fundamentally uncomfortable with the premise that the question deserves formalization at all. But December will provide data regardless of comfort levels. When 3 Atlas makes its closest approach to Earth, when telescopes capture their highest resolution observations, when spectroscopic measurements reveal composition in unprecedented detail, we'll know more. Not everything, never everything from telescopic observation alone, but more. And that data will either reinforce the natural explanation, as most scientists expect, or it will reveal anomalies that previous observations missed. Are there outcome advances, understanding? Are there resolved narrows uncertainty? The important thing, the scientifically necessary thing, is that we look carefully enough to distinguish between the two possibilities. Chapter 8. What the Mars images revealed. On October 3rd, 2025, NASA's Mars Reconnaissance Orbiter executed a carefully planned observation sequence, pointing its Odyssey camera designed to photograph the Martian surface at resolutions fine enough to distinguish features smaller than a meter toward 3 Atlas during the object's closest approach to Mars. Odyssey was never intended for this application. It photographs planetary surfaces from orbital altitudes of a few hundred kilometers, not faint comets tens of millions of kilometers away, but at minimum approach distance of approximately 29 million kilometers. The geometry provided an opportunity no other instrument possessed, the chance to resolve 3 Atlas's nucleus separately from its surrounding coma. The images, when released in late October, showed approximately what astronomers expected: a diffuse, roughly circular coma of gas and dust surrounding a brighter central region. The nucleus itself appeared as an elongated brightness concentration, suggesting either an irregular shape or possibly a close binary pair to objects orbiting each other, a configuration seen in perhaps 15% of comets. Resolution at that distance translated to roughly 30 kilometers per pixel. For an object whose nucleus measures somewhere between 5 and 10 kilometers across, that means the solid core occupied perhaps 1 pixel at best. Possibly a fraction of a pixel, insufficient to reveal surface features, barely adequate to confer size estimates derived from other observations. NASA's official statement emphasized the technical achievement: first direct imaging of an interstellar object's nucleus from another planet, while carefully noting that the images showed no features inconsistent with natural cometary structure. Nothing geometric, nothing obviously artificial, nothing requiring extraordinary explanation. Most news coverage framed the observations as confirmation: 3 Atlas is a comet. Unusual in some respects, but fundamentally natural. The story cycle moved forward. Public attention shifted, but within the astronomical community, discussion continued around a detail that didn't quite fit expectations. The brightness distribution in the coma wasn't symmetrically centered on the nucleus. In typical comets, outgassing produces a coma that's densest near the nucleus and gradually diffuses outward. You see concentric shells of material, sometimes jet structures, but generally the brightness peaks at the central solid body and decreases with distance. It's basic physics. Material originates from the surface, disperses into space, follows. Ballistic trajectories determined by gravity and radiation pressure. The higher IC images showed something subtly different. The brightest region of the coma appeared offset from the nucleus by approximately 50 kilometers, about 1.5 pixels in the images, toward the sunward side, not dramatically off-center, but measurably asymmetric. Several explanations exist for this observation. Jets of material could be erupting preferentially from the sunward hemisphere, creating denser concentrations of dust and gas in that direction. Rotation could be carrying active regions into sunlight, producing periodic bursts that create asymmetric distributions. The nucleus itself might be fragmented, with pieces separated by distances comparable to the observed offset. All standard cometary behavior, all consistent with natural processes. But there's another interpretation, one that several researchers noted privately, though few published openly. If the nucleus was surrounded by a thin shell of material, perhaps a hollow structure with only the outer surface responding to solar heating, the outgassing would originate from that outer shell rather than from a solid core. And depending on the shell's thickness and how sunlight penetrated it, you might see exactly this kind of offset between where the brightness appears and where the actual solid structure lies. This wasn't evidence of artificiality. It was barely even an anomaly, more of a curiosity, something that fit less obviously into standard models than most cometary observations. But that didn't clearly contradict them either. NASA scientists who analyzed the images spent significant time investigating this offset. They concluded that it fell within the range of variations seen in irregular outgassing from active comets, that the resolution limitations made precise localization difficult, and that no extraordinary explanation was required. The images were archived. Papers describing the observations would be published in coming months, and that, for most of the astronomical community, closed the question. Yet the offset remained documented, measured, unexplained, not in the sense of being inexplicable, but in the sense that no single explanation emerged as obviously correct to the exclusion of alternatives. It was one more small strangeness added to an accumulating collection. Chapter 9. The Silence from Radio Telescopes. In August 2025, shortly after 3 Atlas's discovery, several researchers proposed dedicating radio telescope time to listening for potential signals from the object. Not because there was specific evidence suggesting technological origin, but because the opportunity cost of listening was minimal, while the potential value, however improbable, was enormous. The Breakthrough Listen initiative, funded by Yuri Milner and focused on searching for evidence of extraterrestrial technological civilizations, seemed like a natural fit. They had dedicated time on major facilities including the Green Bank Telescope in West Virginia and the Parkes Telescope. In Australia, adding 3 Atlas to their target list would require only modest schedule adjustments. As of December 2025, no results from such observations have been publicly released. This could mean many things. It could mean observations were conducted and detected nothing, with null results considered insufficiently interesting for immediate publication. It could mean observations are planned but haven't yet been scheduled due to competing demands for telescope time. It could mean proposals were submitted but not accepted because program committees viewed them as low scientific priority. Or it could mean observations were conducted and detected, something requiring careful analysis before public announcement. The challenge with interpreting silence is that silence itself carries no information. We can't distinguish between we looked and found nothing and we didn't look, and we looked and are still analyzing what we found without explicit statements from the facilities involved. Avi Loeb has noted publicly that he's aware of no systematic radio monitoring of 3 Atlas, which he describes as a missed opportunity regardless of ultimate conclusions about the object's nature. Radio observations cost relatively little, provide data that can either rule out artificial signals definitively or detect them unambiguously, and create a baseline for future interstellar objects that will inevitably be discovered in coming years. The argument for listening is straightforward. If 3 Atlas were a probe, despite the low probability most scientists assign to this possibility, it might transmit signals for multiple purposes: navigation beacons, data transmission. Back to its origin point, communication attempts with any technological civilizations in this system, or simply routine telemetry. The electronic equivalent of the constant, low-level signals every spacecraft humanity has built emits as part of normal operations. Natural objects don't transmit radio signals in narrowband frequencies. Stars and planets and nebulae all emit radio waves as thermal noise, but it's spread across broad frequency ranges without the focused, structured characteristics that indicate technological origin. A single detection of narrowband emissions from 3 Atlas at any frequency would constitute extraordinary evidence requiring extraordinary scrutiny, but ultimately providing near certainty about artificial origin. The absence of such detection, conversely, proves very little. An artificial probe not actively transmitting or transmitting in directions that don't intersect Earth, or using communication methods will lack technology to detect, would be indistinguishable from a natural object through radio observation. So, the silence from radio telescopes, assuming observations were actually conducted, tells us only that if 3 Atlas is artificial, it's not broadcasting signals we can detect with current instruments and methods, which is precisely what we'd expect from either a natural object or a technological one designed for discrete operation. Still, the apparent lack of systematic radio monitoring represents a curious gap in our investigation of the most statistically unusual interstellar object discovered to date. Not evidence of conspiracy or concealment, but evidence of institutional inertia, of scientific conservatism prioritizing established research programs over speculative longshots. Whether that conservatism will later appear prudent or short-sighted depends on what December's optical observations reveal. Chapter 10. The December Window. From December 10th through December 20th, 3 Atlas will pass through the portion of its trajectory that provides Earth's major observatories their optimal viewing geometry. Close enough for detailed observation, far enough that it's not lost. In solar glare, positioned in the night sky where multiple facilities can track it simultaneously, across both northern and southern hemispheres. This 10-day window represents the culmination of 6 months of increasingly detailed studies since the object's discovery. Everything we've learned, the mass estimates, trajectory calculations, spectroscopic measurements, visual observations, has been building toward this moment when we'll gather the highest resolution data possible before 3 Atlas becomes 2. Destined to study effectively, the observations planned include optical imaging from Hubble and ground-based telescopes with adaptive optics, capturing surface features at the finest resolution achievable from Earth's distance. These images will show whether the nucleus appears as a single solid body, a contact binary, a fragmented rubble pile, or something less easily categorized. They'll reveal color variations that might indicate compositional heterogeneity. They'll track rotation period and axis orientation with precision impossible from earlier observations at greater distances, infrared spectroscopy from the James Webb Space Telescope, measuring thermal emission to determine surface temperature distribution. This matters because temperature reveals how efficiently solar radiation is being absorbed versus reflected, which in turn constrains surface composition and structure. A solid rocky object heats differently than a fluffy aggregate of ice and dust. A hollow shell with thin walls would show different thermal response than a solid mass. Ultraviolet observations tracking the production rates of various gas species in the coma: hydroxyl, carbon monoxide, carbon dioxide, cyanide. Each molecule fluoresces at characteristic UV wavelengths when excited by solar radiation. By measuring emission strengths, astronomers can determine not just what's present, but in what quantities and at what rates it's being released. Changes in these rates as the object continues its trajectory will reveal how solar heating affects different regions of the surface. Polarimetry, measuring the polarization state of scattered sunlight. Dust grains of different sizes, shapes, and compositions polarize light differently. These measurements constrain particle properties in the coma, revealing whether the dust resembles typical cometary material or shows anomalies in grain, size distribution, or structure. Photometry, precise brightness measurements across multiple filters. Comets often vary in brightness as they rotate, with different surface regions having different reflectivity. By tracking these variations over time, astronomers can determine rotation period, how fast the object spins, and possibly map regions of different composition on the surface. All of this data, collected simultaneously by multiple independent facilities, will be analyzed by teams around the world over subsequent months. Initial results typically appear within weeks. Refined analysis takes longer. Peer-reviewed papers describing findings in detail usually publish 6 to 12 months after observations, which means even after December's closest approach, even after telescopes have gathered their best data, we'll still be months away from scientific consensus about what this data reveals. But there are questions these observations can answer definitively. Regardless of how long analysis takes, is the trajectory consistent with purely gravitational motion, or do we see evidence of course corrections? If non-gravitational acceleration is detected at levels inconsistent with the observed outgassing, that would indicate either vastly incorrect assumptions about the object's mass or the presence of forces acting on it, beyond simple cometary jet effects? Does the rotation appear stable and natural, or chaotic and possibly controlled? Natural objects tumbling through space for millions of years typically develop stable rotation states determined by their shape and mass distribution. Artificial objects might rotate differently, especially if maintaining specific orientations. Relative to the Sun or other reference points, are there surface features that can't be explained through natural weathering and impact processes? At the resolution available during closest approach, perhaps a few hundred meters per pixel for the best instruments. Geometric regularity or structural organization would be visible if present on the scale of the entire nucleus. Does the outer pattern show evidence of focused jets that might indicate preferential venting from specific locations? Or does it appear diffuse and symmetric as expected from an irregularly shaped rotating body? This matters because artificial objects might vent gases in controlled ways, while natural comets typically have more random distributions of active regions. None of these observations will prove artificiality. Natural objects can display surprising behavior. Comets are complex, messy, unpredictable, but systematic anomalies across multiple independent measurements. If they appear, would elevate the questions surrounding 3 Atlas from statistical curiosities to genuine scientific puzzles, requiring explanation. And that's what December offers. The best opportunity we'll have to either firmly establish this object as a natural, if unusual, interstellar comet, or to document anomalies that future visitors to the solar system might help us understand when we eventually develop technology capable of intercepting and studying such objects directly rather than observing them from millions of miles. Chapter 11. What we still don't know. Despite 6 months of observation by some of the most sophisticated instruments humanity has built, fundamental questions about 3 Atlas remain unanswered. Not because we lack curiosity or capability, but because certain questions can't be resolved through telescopic observation alone. Internal structure. We cannot see inside objects from millions of miles away. All our instruments measure surface properties, reflected light, emitted gas, thermal radiation. Whether the nucleus is solid, fractured, or hollow remains undetermined. Whether it's homogeneous or contains internal voids, chambers, or differentiated layers cannot be established without close-range radar or seismic probing, neither of which current missions can provide. True composition. Spectroscopy reveals what gases are being released from the surface as it heats. It doesn't tell us what's beneath those surface layers. A technological object coated in ice and dust would release the same molecules as a natural comet during solar heating. We detect water, carbon dioxide, organic compounds, everything. We're currently observing without being able to distinguish surface frost from bulk composition. Origin point. We can trace 3 Atlas's trajectory backward through space, but interstellar distances and timescales prevent identifying a specific parent star system. The object could have traveled for millions of years from any of thousands of stars in the galactic neighborhood. Could be truly ancient, older than our solar system, ejected when the Milky Way's chemistry differed from present conditions. Purpose, if any. This is perhaps the most fundamental unknown. If 3 Atlas is technological, a possibility most scientists consider vanishingly unlikely, but cannot completely exclude. We have no framework for understanding its mission. Exploration, resource assessment, survival mission from a dying civilization, automated probe, continuing operations long after its creators vanished. The range of possibilities is limited only by imagination. And imagination provides poor guidance when extrapolating from a sample size of 1. These unknowns matter because they define the limits of what December's observations can reveal. We will get better data, higher resolution images, more precise spectroscopy, refined trajectory measurements. We will narrow uncertainty in multiple parameters. But we cannot, from Earth, definitively determine whether 3 Atlas is natural or artificial through remote sensing alone. That question requires either detection of unambiguous signals, radio transmissions, visible propulsion, geometric surface features at scales our telescopes can resolve, or eventual direct investigation. With spacecraft capable of close approach, neither seems likely in the immediate future. The closest approach on December 15th places 3 Atlas at 1.8 astronomical units from Earth, about 170 million miles. No existing mission has trajectory or propulsion capability to intercept it. Designing, building, and launching a probe to rendezvous with an object moving at 67 kilometers per second relative to the Sun would require years of preparation and enormous cost, justifiable only if initial observations revealed characteristics so anomalous that international cooperation on an emergency basis became politically feasible. Current observations, while unusual in aggregate, do not rise to that threshold. They show a massive object with improbable trajectory alignment, releasing gases consistent with cometary composition. Strange. Yes. Inexplicable. No. So December's window represents our best and likely final opportunity to study 3 Atlas in detail before it continues its journey back into interstellar space, possibly never to be observed again by human eyes or instruments. What we learn in those 10 days will shape how we approach future interstellar visitors. If 3 Atlas proves thoroughly ordinary despite initial statistical peculiarities, the lesson will be that improbable trajectories sometimes occur through chance alone, that massive interstellar objects may be less rare than current models suggest, and that unusual chemistry can emerge from formation environments we've never directly sampled. If anomalies persist in December's data, if observations reveal features that resist straightforward natural explanation, the lesson will be different. That we need better frameworks for investigating objects whose characteristics don't fit established patterns. That statistical improbabilities deserve systematic follow-up rather than casual dismissal. And that the question, could this be artificial, deserves methodological rigor rather than reflexive rejection. Either outcome advances scientific understanding, either result provides data for evaluating future discoveries, but only one outcome persistent. Documented anomalies that accumulate into a pattern suggesting intent rather than chance would fundamentally alter humanity's understanding of its place in the cosmos. Chapter 12. The pattern we might be missing. Consider a thought experiment. Imagine you're an astronomer in the year 1950. Before we had spacecraft, before we understood planets around other stars, before we knew whether technological civilizations might be common or rare in the universe. You're observing the night sky with the best telescopes available, already quite good, capable of detecting faint objects and measuring spectra when you notice something unusual passing through the solar system. It's moving fast, clearly not bound to the sun. Its trajectory is oddly aligned with the plane of planetary orbits. It shows faint outgassing that might be cometary, but the chemical composition seems slightly off. The mass appears higher than expected for the observed size, and curiously, it passes near Earth at a suspiciously convenient distance for observation. You note these oddities. Perhaps you publish a paper describing the unusual characteristics, but you have no framework for interpreting them as potentially artificial. The idea that technological objects from other star systems might visit ours hasn't entered serious scientific discourse. SETI won't exist for another decade. The very concept of investigating the question systematically hasn't been developed. So you classify it as an unusual comet. Note the peculiar features in the literature and move on to other observations. The object leaves the solar system. One never sees it again, and humanity's first potential encounter with extraterrestrial technology passes, unrecognized because we lacked the conceptual framework to ask the right questions. This scenario isn't speculation about the past. We have no evidence anything like this actually occurred in 1950. It's a parable about the present. We now possess sophisticated instruments. We have detailed models of how comets and asteroids form and behave. We understand spectroscopy, orbital mechanics, thermal physics. We've sent spacecraft to study comets up close. We know what natural objects should look like across a wide range of conditions, but we still lack a systematic framework for recognizing artificial objects. If they're designed not to obviously advertise their nature, we have no established protocols for what observations would definitively distinguish natural from technological origin in objects that don't transmit radio signals or display overtly geometric structures. This is the pattern we might be missing. Not that every unusual object is artificial, but that our methods for recognizing artificiality are optimized for detecting only the most obvious cases, radio signals, clearly geometric shapes, visible propulsion, while potentially overlooking more subtle indicators. 3 atlases: statistical profile, improbable trajectory, unusual mass to outgassing ratio, convenient timing, chemical peculiarities, doesn't prove artificiality, but it represents exactly the kind of aggregate signature that would appear if an object were designed to mimic natural phenomena while still accomplishing specific mission parameters like surveying inner planets or using gravitational assists from planetary encounters. A truly advanced civilization building interstellar probes wouldn't necessarily design them to be, obviously, artificial. Depending on mission objectives, discretion might be advantageous. A probe coated in cometary ice, using natural outgassing for minor course corrections. Maintaining external characteristics indistinguishable from debris would accomplish close approach to inhabited worlds without triggering defensive responses or unwanted attention. This doesn't mean 3 Atlas is such a probe. The natural explanation remains vastly more probable given base rates. The overwhelming majority of objects in space are natural, full stop. But it means we should be thoughtful about what observations would actually distinguish between the scenarios rather than assuming that current observations definitively resolve the question simply because they're consistent with natural formation. The December observations provide an opportunity to gather data that might help develop those distinguishing criteria. Not to prove 3 Atlas is artificial. That would require far more dramatic anomalies than seem likely, but to establish baselines for evaluating future interstellar visitors when they appear, and they will appear. The Vera Rubin Observatory will find them regularly. We'll detect dozens, then hundreds, then thousands. Over coming decades, most will be natural. But if technological probes are even moderately common relative to ejected planetary debris, say, 1 artificial object for every 1,000 natural ones will encounter them. The question is whether we'll recognize them when we do. Chapter 13. What December might tell us. The observations planned for mid-December will answer some questions while inevitably raising others. This is how science proceeds, not through sudden revelations that settle all uncertainties, but through incremental refinement of understanding that narrows the range of plausible explanations. What we will definitely learn: precise trajectory. With observations from multiple facilities over the optimal viewing period, orbital parameters can be determined to extreme accuracy. If course corrections occurred at perihelion, they'll become apparent in deviations from purely gravitational motion. If the orbit remains perfectly hyperbolic with no anomalous accelerations that constrain scenarios involving propulsive maneuvering, surface characteristics, higher resolution imaging will reveal whether the nucleus is a single coherent body, a loose aggregate, a contact binary, or something less easily categorized. Color variations across the surface might indicate compositional differences. Brightness variations during rotation will constrain shape and potentially reveal non-random features if they exist at detectable scales. Outgassing behavior continued. Spectroscopic monitoring will track how gas production rates evolve as the object moves away from perihelion. Natural comets show predictable patterns determined by solar heating and rotation. Deviations from expected patterns, gas production increasing when it should decrease, emissions from regions that should be cold and inactive, abrupt changes not correlated with rotation or solar distance would be worth examining carefully. Thermal properties. Infrared observations will measure how the surface responds to solar heating. This constrains bulk properties. Solid objects heat and cool differently than porous aggregates. Icy surfaces behave differently than rocky ones. If the thermal signature doesn't match composition inferred from spectroscopy, that mismatch would require explanation. What we won't learn, regardless of observation quality, internal structure. Short of radar penetration or seismic probing, we cannot determine whether 3 Atlas is solid throughout, contains voids, or possesses organized internal architecture. The surface properties we measure don't uniquely specify interior configuration, ultimate origin. Trajectory tracing backward through interstellar space becomes increasingly uncertain over long time scales. While we can determine the general direction 3 Atlas came from, identifying a specific parent star system among thousands of candidates exceeds current capability, intent, if any. No passive observation can determine whether an object is following a programmed mission, responding to detected conditions, or simply obeying physical laws applied to inanimate matter. Purpose, if it exists, remains invisible to telescopes. The gap between what we can observe and what we wish we could know defines the frustration surrounding 3 Atlas. We have a genuinely unusual object passing through our neighborhood at the closest distance any confirmed interstellar visitor has achieved. We have sophisticated instruments capable of characterizing it in unprecedented detail. And yet the fundamental question, is this something natural or something made, may remain unanswerable from remote observation alone. This doesn't mean the observations lack value. Understanding what natural interstellar objects look like provides the baseline for recognizing anomalies when they appear. Documenting the chemical composition and structure of material from other star systems teaches us about planetary formation in environments we can never directly sample. Even if 3 Atlas proves thoroughly ordinary, the data contributes to understanding we didn't possess before its arrival. But there's a nagging possibility that bothers some receptorist lobe prominent among them. The possibility that we're gathering extensive data on an object whose true nature won't become apparent until we either develop technology to investigate it directly, which won't happen in time before it leaves the solar system, or until we've observed enough similar objects to recognize patterns currently invisible in a sample size of 3. December represents that moment when we extract maximum information from this particular visitor before it recedes beyond effective observation. Whether that information resolves current questions or simply refines them into new forms won't be clear until analysis completes months from now. In the meantime, the object continues its trajectory, moving outward, carrying whatever secrets it holds, natural or otherwise, back into the vast dark between stars. Chapter 14. After December. By January 2026, 3 Atlas will have passed its closest approach to Earth and will be receding into the outer solar system, headed generally toward the orbital region of Jupiter. By March, it will pass within 0.36 astronomical units of Jupiter, close enough that NASA's Juno spacecraft, currently orbiting the gas giant, might be able to observe it with onboard instruments if mission controllers choose to dedicate observation time during what would otherwise be focused on Jupiter itself. That March observation would provide the last equality data before 3 Atlas becomes too faint and distant to study effectively. After Jupiter, the trajectory carries the object outward beyond the realm of effective ground-based or orbital telescope observation. Within a year or 2, it will be too dim to track. Within 5 years, it will be hundreds of from the Sun, well into the outer reaches where only the largest, brightest objects remain visible from Earth. And then it's gone, lost in the immensity of interstellar space, perhaps to encounter another star system in 1,000,000 years, perhaps to drift indefinitely through the cosmic dark, perhaps, if it's technological and merely hibernating, to activate again when conditions warrant. We won't know. We'll have whatever data we gathered during its 6-month passage through the inner solar system. We'll have papers analyzing those observations, debates about interpretation, refined models of interstellar object populations. We'll have learned things about cometary, chemistry, orbital dynamics, and possibly, depending on what anomalies. The December data reveals about the limits of our ability to distinguish natural from artificial when observing from afar. The 3, Atlas itself will be beyond reach. Whatever questions it raised but didn't answer will remain unresolved until future visitors provide additional data points for comparison, and there will be future visitors. The discovery rate for interstellar objects is accelerating rapidly. In the 8 years between Oumuamua's discovery in 2017 and now, we've confirmed 3. The Vieira-Rubin Observatory's survey capacity suggests we'll find 1 every few months once the system reaches full operational capability. Within a decade, we might have catalogued hundreds. Most will be small hundreds of meters across, perhaps a few kilometers. Most will pass through the outer solar system where observation is difficult. Most will be discovered only in hindsight, after they've already made their closest approach and are heading back into interstellar space. But occasionally, one will be large. Occasionally, one will pass near Earth. Occasionally, one will display characteristics unusual enough to warrant the kind of scrutiny 3 Atlas has received. And each one will teach us something about how to approach the question that mainstream science remains reluctant to ask systematically. How would we recognize a technological object if one appeared? This is 3 Atlas's real legacy, regardless of what it ultimately proves to be. It forced the conversation. It made respectable scientists consider scenarios they would normally dismiss. It demonstrated that statistical improbabilities can cluster around single objects in ways that demand more than casual acknowledgement. The question isn't whether 3 Atlas is a probe from an alien civilization. The probability remains low. The evidence remains ambiguous. The natural explanation remains vastly more likely. The question is whether we're prepared institutionally, methodologically, conceptually to recognize the technological object when it eventually arrives. Because if technological civilizations exist anywhere in our galaxy, if they've developed interstellar flight capabilities, if they've sent automated probes to survey neighboring star systems, then statistically, sooner or later, one of the objects we detect passing through our solar system will be artificial. Not soon, perhaps. Maybe not for decades or centuries, but eventually. And when that moment comes, when we're observing something that's genuinely not natural, will we recognize it, or will we classify it as an unusual comet? Note the peculiarities in academic papers. And what should leave without understanding what we've seen? Chapter 15. The thing about certainty. There's a particular kind of frustration unique to astronomy. You observe objects millions or billions of miles away. You gather data, images, spectra, brightness, measurements. You apply physics, mathematics, statistical analysis, and you build models describing what you're seeing, but you can never truly know. You can never reach out and touch the object, examine it directly, probe its interior, verify your conclusions through hands-on investigation. You can only observe from a distance and infer. This limitation shapes how astronomers think about certainty. In laboratory sciences, you can run experiments repeatedly, vary conditions, test hypotheses directly. In astronomy, you get one observation per event, one supernova, one planetary transit, one close approach of an interstellar object. You can't rerun it. can't ask the object to pass by again more slowly so you can get better data. You work with what you get. For 3 Atlas, what we get is 6 months of observation as it passes through the inner solar system. 6 months during which it's close enough and bright enough to study. Then it's gone and we're left with whatever data we manage to collect, whatever questions we manage to answer, whatever mysteries remain unsolved. This creates a particular kind of pressure. Every observation matters because there won't be another chance. Every decision about which instrument to use, which wavelength to observe, which questions to prioritize, these decisions have consequences that can't be undone later the December. Observations carry that weight. They're not just another data point in an ongoing study. They're the final opportunity to gather high-quality information before the object recedes beyond effective observation range. And yet, even with perfect execution, even with every major telescope performing flawlessly and gathering data exactly as planned, we'll still be left with uncertainty about fundamental questions. Is it natural or artificial? We'll have better data for evaluating that question, but unless the observations reveal unambiguous artificiality, geometric structures, radio signals, obvious propulsion, the question won't be definitively resolved. It will simply become a more informed version of the same uncertainty we've had since July. What's it made of internally? We'll know surface composition with high precision. We'll have thermal models constraining bulk properties, but internal structure will remain inferred rather than directly measured. Where did it come from? We'll have trajectory traced backward through space, perhaps identifying the general region of the galaxy, possibly narrowing to a few candidate star systems, but we won't know for certain which star, which planetary system, which formation, environment produced this particular object. These limitations don't represent failure. They're inherent to observational astronomy. You learn what you can learn from photons that've traveled millions of miles to reach your instruments. Everything else is inference, modeling, educated guessing, constrained by physical laws, but never rising to the level of proof available in experimental sciences. So when December passes, when the observations are complete and analysis begins, we'll be in a familiar situation. We'll know more than we did. We won't know everything we wish we could. And we'll be making probabilistic judgments about competing explanations rather than reaching definitive conclusions. For most scientists, this is acceptable. Science doesn't require absolute certainty. It requires honest evaluation of evidence and willingness to revise conclusions when new data arrives. If December's observations show 3 Atlas behaving exactly as a large carbon dioxide-rich comet should behave, outgassing predictably, rotating naturally, displaying no anomalous accelerations or structural features, then the scientific consensus will solidify around the natural explanation. The statistical improbabilities will be filed away as interesting coincidences, reminders that unlikely events do occasionally occur in a universe vast enough to contain countless possibilities. If the observations reveal persistent anomalies, trajectory deviations unexplained by outgassing, thermal signatures inconsistent with composition, structural regularities suggesting non-random organization, then the conversation continues. Papers will debate interpretations. Some researchers will argue for exotic, natural explanations. Others will suggest the data warrants consideration of artificial origin. The question won't be settled. It will simply move to a new phase of investigation, constrained by whatever data December provides. This is how science works. When dealing with unique events that can't be replicated or directly tested, you gather the best data possible. You analyze it rigorously. You argue about interpretation. And eventually a consensus emerges, not because everyone agrees absolutely, but because one explanation accounts for more observations more eloquently than alternatives. But there's something unsettling about that process when applied to objects like 3 Atlas, the consequence of being wrong, of dismissing a genuinely technological visitor as a natural comet. Because we lacked sufficient imagination or observational capability, seems vastly more significant than the consequence of being too cautious, of investigating a natural object. To thoroughly dot this asymmetry haunts the debate. Those arguing for natural explanations point out correctly that extraordinary claims require extraordinary evidence. They note that we've never confirmed detection of extraterrestrial technology. Despite decades of searching, they observe that comets are complex, unpredictable objects whose behavior often surprises us without requiring alien engineering. They argue that invoking artificiality without definitive proof damages scientific credibility and encourages conspiracy. Thinking among the public, all valid concerns, all reflecting legitimate scientific values. But those arguing for more careful investigation countered that the cost of a false positive, studying a natural object as if it might be artificial, is merely wasted time and resources. Whereas the cost of a false negative, dismissing an artificial object as natural, is a missed opportunity that will never return. 3 Atlas won't pass by again. We won't get a second chance. This isn't an argument that can be resolved through pure logic. It's a value judgment about acceptable risk in the face of uncertainty. How much caution is appropriate when investigating something unprecedented? How much skepticism is productive before it becomes closed-mindedness? Different scientists answer differently based on temperament, training, and assessment of probabilities. Some lean toward conservatism, requiring overwhelming evidence before entertaining unconventional hypotheses. Others lean toward exploration, considering possibilities that most dismiss as unlikely because the potential significance outweighs low probability. Neither approach is wrong. Both serve important functions in how science advances. Conservatism prevents wild goose chases and maintains standards of rigor. Exploration prevents missing genuinely revolutionary discoveries by looking only where conventional wisdom suggests looking. The tension between these approaches shapes the December observations. Conservative astronomers will gather data focused on confirming natural cometary characteristics, rotation period, outgassing rates, composition profiles. Exploratory astronomers will gather data searching for anomalies, trajectory deviations, structural regularities, emission patterns inconsistent with natural processes. Ideally, both approaches examine the same data from different perspectives. And if the object is natural, the conservative interpretation will fit observations better. If it's artificial, the exploratory interpretation will identify features the conservative approach would. overlooked dot, but this ideal scenario assumes the data will be clear enough to distinguish between interpretations definitively. In practice, astronomical observations are messy. Instruments have limitations. Observations contain noise. Alternative explanations can often account for the same features through different mechanisms, which means December's data, however comprehensive, will likely still leave room for debate. The conversation will continue beyond the observations themselves into analysis, interpretation, peer review, and eventually into the scientific consensus that takes months or years to solidify. And by then, 3 Atlas will be gone, receding into interstellar space, carrying whatever truths it represents beyond our ability to investigate further. Chapter 16. What it means if we're wrong. Consider 2 scenarios. Scenario 1, 3 Atlas is natural. It's a massive comet ejected from a distant planetary system during formation, wandering through interstellar space for millions of years before its trajectory happened to carry it through our solar system. The statistical improbabilities trajectory, alignment, planetary encounters, perihelion timing are genuine coincidences, unlikely but not impossible, in a galaxy containing billions of star systems, each potentially ejecting material. The mass is high because it formed in an unusually dense region of its parent system's protoplanetary disk. The chemistry is odd because that system had different elemental abundances than ours. The trajectory aligned with our ecliptic plane through pure chance. The timing placed perihelion during solar conjunction by accident of orbital mechanics. In this scenario, December's observations confirm natural behavior. Papers are published documenting the unusual characteristics. Models are refined to accommodate greater diversity in interstellar object populations. The episode becomes a footnote. In astronomical history, an interesting object that briefly raised questions but ultimately fit within natural parameters. The researchers who suggested artificial origins are remembered as having pursued a speculative hypothesis that data didn't support. Their careers aren't destroyed. Science allows for wrong ideas, as long as they're proposed seriously and abandoned when evidence contradicts them, but they're reminded by colleagues that extraordinary claims require extraordinary evidence. And the evidence never materialized. Life continues. Humanity's understanding of its place in the cosmos remains unchanged. We're still alone, or at least still without confirmed contact with other technological civilizations. The search continues through SETI's radio telescopes and future interstellar observations. But 3 Atlas isn't part of that story. It was just a rock. Scenario 2. 3 Atlas is artificial. It's a probe built by an extraterrestrial civilization and sent to survey star systems in the galactic neighborhood. Its trajectory was designed to pass near multiple planets for observation or resource assessment. Its mass represents engineered structure, a shell containing instruments, propulsion, perhaps hibernating systems waiting for specific triggers. The surface coating of ice and dust accumulated during interstellar travel, providing thermal protection and making the object appear natural to casual observation. The outgassing we've measured comes from that surface layer, responding to solar heating exactly as a comet's would. But beneath it lies technology we don't have instruments to detect from millions of miles away. The perihelion timing during solar conjunction wasn't coincidence. It was planned. The object made course corrections behind the sun while Earth couldn't observe, using propulsion systems so efficient they don't produce obvious exhaust plumes. It's now on a modified trajectory, perhaps captured into a long elliptical orbit, perhaps heading toward a specific destination in the outer solar system where it will conduct extended observations. In this scenario, December's observations might or might not reveal the truth. If the probe is designed for discretion, if its creators understood that inhabited systems might have technological civilizations capable of detection, they would have ensured it could pass as natural. The observations might show subtle anomalies, trajectory deviations slightly larger than outgassing can explain, thermal signatures that don't quite match composition, structural hints of regularity, but nothing definitive, nothing that would convince skeptics. And so humanity watched the object recede, having documented something genuinely extraordinary without recognizing it. Future historians, when the truth eventually becomes clear, perhaps through detection of other probes, perhaps through direct contact with the civilization that built them, will look back at December 2025 as the moment we had the chance to understand and failed to ask the right questions. The researchers who suggested artificial origins will be vindicated, but decades too late. Their caution was appropriate. Their willingness to consider improbable possibilities was exactly what the situation required. But they were dismissed by a scientific community too wedded to parsimony, too reluctant to entertain ideas that seemed to border on science fiction. The cost of error. These scenarios represent the two ways we could be wrong about. 3. Atlas. Either it's natural and we're wasting energy investigating artificial hypotheses, or it's artificial and we're missing the most significant discovery in human history, because we're too quick to assume narrowly is. The costs of these errors are not symmetric. If we investigate thoroughly and conclude the object is natural, we've spent telescope time and research effort. We've published papers that will be read by small audiences of specialists. We've had debates at conferences. We've refined our understanding of interstellar objects. These are normal scientific activities with normal costs. If we investigate casually and miss that the object is artificial, we failed to recognize evidence of extraterrestrial intelligence when it passed within 170 million miles of our planet. We've watched a probe from another civilization traverse our solar system and dismissed it as a rock. We've demonstrated that humanity, even with sophisticated technology and extensive scientific knowledge, lacks the conceptual framework to identify artificial objects that don't advertise themselves obviously, and we won't get another chance with this particular object. It will leave, we'll never see it again. Whatever information it carried, whatever purpose it served, whatever we might have learned from recognizing it correctly, all lost because we assumed too quickly that the simplest explanation must be correct. This isn't an argument that 3 Atlas is definitely artificial. The probability remains low. The natural explanation remains more parsimonious, given what we know about base rates, how many objects in space are natural versus how many might be technological, but it's an argument for asymmetric caution, for taking seriously the possibility that deserves serious investigation even if ultimately for gathering data comprehensive enough that future scientists, looking back at December 2025, won't be able to accuse us of having observed something extraordinary and not bothering to look carefully. Chapter 17. The Institutional Gap. In October 2025, shortly after 3 Atlas reached perihelion behind the Sun, Avi Loeb published an essay arguing for the establishment of an international organization, specifically tasked with investigating interstellar objects for potential technological signatures. The proposal wasn't new. He'd been advocating for something similar since Oumuamua's discovery in 2017, but the arrival of 3 Atlas, with its unusual characteristics and convenient timing, gave the argument renewed urgency. The core premise: we currently have no systematic framework for evaluating whether objects entering our solar system might be artificial. NASA tracks near-Earth objects that could pose collision risks. Various space agencies coordinate on planetary defense. SETI organizations search for radio signals from distant stars, but there's no body responsible for the specific question of whether physical objects passing through our neighborhood might be technological in origin. This creates a gap in our institutional response capabilities. When an unusual object appears, individual researchers can propose observations, write papers, make arguments, but there's no coordinated international effort, no pool of resources specifically allocated to thorough investigation, no protocol for what constitutes sufficient evidence to elevate an object from probably natural to deserving intensive scrutiny. Loeb's proposed organization would serve several functions. Triage: rate each newly discovered interstellar object on a scale, from clearly natural to potentially artificial, based on observable characteristics. Objects rating above a certain threshold would automatically trigger coordinated observation campaigns using multiple facilities worldwide. Coordination: pool data from observatories across national boundaries ensured that telescopes in different hemispheres operating at different wavelengths using different techniques all contribute observations to a centralized database accessible to researchers globally. Protocol development: establish clear criteria for what observations would distinguish natural from artificial. Define falsifiable predictions. Create standardized methodologies so that conclusions drawn by different teams can be compared meaningfully. Rapid response: maintain readiness to redirect resources quickly when something truly anomalous appears. Interstellar objects move fast. The window for observation is brief. An institutional framework capable of mobilizing major facilities within days rather than weeks could mean the difference between gathering definitive data and missing the opportunity. Communication: provide authoritative, scientifically grounded information to the public and policymakers. Prevent both premature claims of discovering alien technology and premature dismissals of legitimate anomalies. The response from the broader astronomical community has been mixed. Some researchers support the concept, arguing that systematic investigation of interstellar objects makes sense, regardless of how likely artificial visitors might be. The science of understanding natural interstellar debris would benefit from coordinated effort even if no probe is ever discovered. Others object that formalizing this kind of investigation legitimizes speculation better left to fringe groups. They worry that an official organization investigating alien probes would damage astronomy's public credibility, attract conspiracy theorists, and waste resources on questions with near-zero probability of positive answers. Still, others point out practical difficulties. Who would fund such an organization? Which countries would participate? What happens when observations suggest something potentially artificial but not definitively so? Does the organization issue alerts, make recommendations, try to communicate with the object? These aren't trivial concerns. International scientific cooperation is valuable, but often difficult to coordinate. National interests, funding priorities, and political considerations complicate even straightforward collaborations. Adding the loaded question of potential extraterrestrial contact makes everything more ad hoc approach works adequately when objects are clearly natural. But it risks missing anomalies that would be apparent if data were pooled and analyzed systematically. It creates situations where one group sees something unusual but doesn't realize it's significant because they lack context from other observations conducted independently. For 3 Atlas specifically, we'll never know if more coordinated observation might have revealed features that individual groups missed. The December window will provide concentrated attention, but by then the object has already made perihelion, already passed Mars, already completed the portions of its trajectory where course corrections might have been most likely. Ideally, an institutional framework would have been in place before 3 Atlas appeared. The object would have been flagged immediately upon discovery based on its unusual trajectory. Resources would have been allocated automatically. Observations would have been coordinated from July through December, ensuring no critical opportunities were missed. Whether such an organization will ever exist remains uncertain. Scientific institutions change slowly. International cooperation requires diplomatic effort. Funding for speculative research competes with established priorities, but the need is real. We're entering an era where interstellar objects will be detected routinely. Some will be unusual, some will raise questions. And unless we develop systematic methods for investigating those questions, we risk either dismissing genuine anomalies prematurely or chasing spurious signals without proper methodology. 3 Atlas. Regardless of what it ultimately proves to be, has demonstrated the need for better frameworks. December's observations will show whether current ad hoc approaches were sufficient. If they weren't, if we missed something important because no one was coordinating efforts systematically, perhaps that failure will provide the impetus for institutional change. Chapter 18. The Dark Forest Hypothesis. There's a particular thought, experiment in astrobiology, that shapes how some researchers think about interstellar visitors. It's called the Dark Forest Hypothesis, popularized by Chinese science fiction writer Liu Cixin, but originating in earlier work on game theory and existential risk. The premise is simple and chilling. The universe might be full of intelligent civilizations, but they all remain silent and hidden because revealing your presence is dangerous. Here's the logic. You can't know the intentions of alien civilizations. They might be peaceful, but they might not. They might claim to come in peace while planning conquest. They might have ethical frameworks so different from yours that what they consider reasonable, behavior you would consider monstrous. You also can't know their capabilities. A civilization capable of interstellar travel likely possesses technology far beyond your own. If conflict arose, you would be hopelessly outmatched. Given these uncertainties, the safest strategy might be to stay hidden. Don't transmit signals into space that reveal your location. Don't respond to signals you detect from others. Don't make yourself a target. And if you do detect signs of another civilization, the coldly rational choice might be to eliminate them before they can locate you and decide you're a threat. Strike first from a position of advantage rather than risk them striking first later when they've had time to assess your capabilities. This creates a universe where everyone is hiding, everyone is listening, and everyone is ready to destroy anyone they find before being destroyed themselves. A dark forest where predators stalk in silence, where making noise means death, where the only safe strategy is invisibility. The hypothesis provides one possible answer to the Fermi paradox, the question of why, if intelligent life is common in the universe, we don't see obvious evidence of it everywhere. Maybe we don't see it because civilizations that reveal themselves don't survive long enough to become obvious. It's a grim scenario. Most astrobiologists consider it unlikely because it assumes universally paranoid behavior inconsistent with how cooperation often emerges as an evolutionary strategy, but it's not impossible. And it shapes how some researchers think about what our response should be if we detect something that might be technological. If 3 Atlas were a probe, and again, this remains highly unlikely. What would that mean in the context of the dark forest hypothesis? One possibility. It's a survey mission, gathering information about star systems in this region of the galaxy. Perhaps it's checking for biosignatures, technological signals, anything indicating inhabited worlds. What it does with that information depends on the intentions of whoever built it. Another possibility, it's already gathering information and transmitting it back to its origin point. We wouldn't necessarily detect those transmissions. They might be tightly beamed in directions we're not monitoring. They might use methods we don't recognize as communication. But years or decades from now, the civilization that sent this probe will know about Earth, about our technology level, about our vulnerabilities. A third possibility, Darko. The probe itself is the weapon. Not a scout sending information back, but an autonomous system making decisions locally. If it detects technological civilizations, if it determines they represent potential future threats, it might already be executing protocols we wouldn't recognize until too late. This isn't paranoia, it's scenario planning. Most researchers consider such scenarios extraordinarily unlikely. Far more likely that 3 Atlas is just a comet. Far more likely that even if artificial probes exist, they're not designed for hostile purposes. Far more likely that civilizations capable of interstellar travel have outgrown destructive impulses, but extraordinarily unlikely isn't the same as impossible. And when dealing with potential existential risks, threats that could affect humanity's long-term survival, even low probability scenarios warrant some level of consideration. So what would appropriate precautions look like? First, careful observation. If 3 Atlas is technological, Understanding its capabilities and behavior patterns provides information about the civilization that built it. Knowledge is the first step in any defensive strategy. Second, discrete monitoring. If the object is transmitting signals, we should be attempting to detect and analyze them. Not necessarily responding that carries its own risks, but listening. Understanding what information might be flowing back to wherever this came from. Third, trajectory tracking. If the object makes course corrections, particularly ones that position it for future interactions with Earth or other planets in our system, that behavior deserves attention. A probe establishing permanent orbit around our Sun, positioning itself for extended observation, represents a fundamentally different situation than one simply passing through. Fourth, preparation. Not military preparation necessarily. We likely couldn't defend against genuinely advanced technology anyway, but conceptual preparation. Working through scenarios, developing response protocols, ensuring that if something truly anomalous becomes apparent, we have some framework for deciding what to do rather than improvising in crises. None of this is happening systematically. There's no government agency tasked with monitoring interstellar objects for potential threats. There's no international protocol for responding. If an object displays characteristics suggesting artificial origin, there's no plan. This might be fine. If 3 Atlas is natural, if all future interstellar objects prove natural, if humanity never encounters alien technology in our cosmic neighborhood, then the absence of such preparation costs us nothing. But if we're wrong, if something technological does appear, the lack of frameworks for recognition and response could prove costly. Not necessarily in immediate physical terms. We're probably not facing independence. Day scenarios where alien spacecraft attack suddenly, but in terms of missed opportunities, poor decision-making under uncertainty or failure to recognize risks until they've already materialized. The dark forest hypothesis is speculative. Most scientists consider it an interesting thought experiment rather than likely reality, but it serves as a reminder that our assumptions about extraterrestrial intelligence, that contact would be peaceful, that advanced civilizations are benevolent, that we have nothing to fear from interstellar visitors, are just assumptions. We have no data. We're guessing based on hope rather than evidence. 3 Atlas almost certainly doesn't require invoking the dark forest hypothesis. It's almost certainly not a probe. It's almost certainly not gathering intelligence about Earth. It's almost certainly not a threat, but almost certainly contains an implicit acknowledgement. There's some probability, however small, that our assumptions are wrong. And observations represent our best opportunity to reduce that uncertainty before the object moves beyond reach. Chapter 19. What the public doesn't know. Throughout the 6 months since 3 Atlas's discovery, most scientific discussion has occurred in specialized forums, conference presentations, peer-reviewed journals, technical preprint servers. The broader public has remained largely unaware that anything unusual is happening. News outlets occasionally report on the object when major observations are announced. Interstellar comet pass near Mars makes for interesting but not alarming headlines. The stories typically mention that it's the 3rd confirmed interstellar object ever detected. Note its size and trajectory. Perhaps include a quote from a researcher saying it's providing valuable insights. interplanetary systems beyond our own. What these articles don't convey, what gets lost in translation from technical papers to public communication, is the genuine strangeness surrounding several aspects of this object: the statistical improbabilities, the mass anomaly, the timing coincidences, the chemical peculiarities. This isn't conspiracy or cover-up. It's the natural result of how science communication works. Journalists interviewing astronomers ask about notable discoveries. Most astronomers, believing three atlases natural, describe it as an unusual but ultimately ordinary comet. They mention interesting characteristics without dwelling on features they consider explainable through standard processes. There is who think the object deserves more careful investigation, as potentially artificial lobe most prominently do get media coverage when they make such arguments. But it's typically framed as controversial speculation from outlier scientists rather than as a legitimate scientific question worthy of serious consideration. This framing affects public perception. Most people reading about 3 Atlas come away thinking there's an interstellar comet passing through. Some scientists think it might be aliens, but most scientists think he's wrong. Nothing to see here, which might be accurate. Probably is accurate. But it means the broader population has no awareness that December's observations carry any particular significance. That there's a genuine scientific question being investigated, rather than just speculative claims from attention-seeking researchers. This creates an interesting dynamic. If December's data confirms natural behavior, the public never needs to know there was any uncertainty. The object was a comet. Scientists studied it. Conclusions were reached. Story over. No harm done by not broadcasting every intermediate debate. But if December's data reveals genuine anomalies, features that even skeptical astronomers can't easily explain through natural processes, then suddenly the public learns that something potentially extraordinary was happening all along and nobody told them. This breeds distrust, conspiracy theories, accusations of cover-up, even when the reality was simply that scientists were waiting for sufficient evidence before making dramatic claims. There's no perfect solution to this communication challenge. Science operates on uncertainty and gradual refinement of understanding. Public communication wants definitive answers. We're not sure yet doesn't make compelling headlines, but 3 Atlas represents a case where the gap between what specialists are debating and what the public knows has become particularly wide. December's observations will either narrow that gap by providing data that settles the question one way or another, or widen it further if anomalies persist without reaching levels that convince skeptics. Either way, the object's closest approach to Earth will occur while most of humanity remains unaware that there's any question about what it is. The telescopes will observe, the data will accumulate, the analysis will proceed, and months later, after 3 Atlas has already receded into the outer solar system, papers will be published, reaching conclusions most people never knew were in doubt. This is normal for astronomy. Most discoveries proceed this way, but there's something disconcerting about the possibility, however remote, that humanity's closest encounter with a potential extraterrestrial probe might occur without anyone outside specialized research communities paying attention until after the opportunity to investigate has passed. Chapter 20. December 15th. on December 10th, 2025. At approximately 14:22 Universal Time, 3 Atlas will reach its point of closest approach to Earth, 1.8 astronomical units, roughly 270 million kilometers, about 170 million miles. In that moment, the object will be moving at approximately 67 kilometers per second relative to the Sun. It will appear as a faint smudge in telescope images, magnitude 15 or 16 depending on current activity levels. Far too dim for naked eye visibility, requiring moderate-sized telescopes even to detect. Its coma will extend perhaps 100,000 kilometers, with a faint tail streaming away from the Sun, barely visible against the background star field. From our perspective, it will cross the constellation Virgo, moving steadily toward the region of sky that contains the galactic center. Within weeks, it will fade below the detection threshold of most ground-based telescopes. Within months, only the largest facilities will be able to track it. Within a year or two, it will be effectively invisible, lost in the vastness of space, beyond our ability to observe. That moment, December 15th at 14:22, represents the culmination of 6 months of anticipation, debate, and preparation. It's the point where 3 Atlas passes nearest to our world, where the geometry provides optimal conditions for observation, where we gather the last equality data before the opportunity vanishes. But the moment itself will be unremarkable. There will be no visible event, no dramatic phenomena, nothing you could point a camera at and capture for posterity. Just an object in space following its trajectory as it has been for millions of years before humans existed, and as it will continue to do for millions of years after we're gone. The significance exists only in context, in the questions surrounding this object, in the data being gathered, in what analysis might reveal in subsequent months. The moment passes like any other, distinguished only by our attention and the meaning we project onto it. December 15th will come and go. Most of Earth's population will have no idea anything occurred. Those tracking the object will note the milestone, file their observations, begin analysis, and 3 Atlas will continue its journey outward, carrying whatever truths it represents beyond our reach. In the end, that's what December means. Not dramatic revelation, not definitive answers, but the point where we stop gathering new data and begin working with what we have, where active observation transitions to analysis and interpretation, where the story of 3 Atlas as an unfolding event becomes the story of 3 Atlas as historical record. What we learn from that record, whether it confirms the natural explanation or reveals surprises that challenge our assumptions, won't be clear until months after December passes. The data must be analyzed, cross-checked, debated, peer-reviewed. Conclusions take time to solidify, longer still to reach consensus. But December 15th represents the end of the observation phase. After that date, we're working with what we managed to capture while the object was close enough to study. No second chances, no do-overs. Whatever questions remain unanswered after December's data is fully analyzed will likely remain unanswered indefinitely. That finality shapes how researchers approach the observations. There's pressure to be thorough, to gather every possible measurement, to ensure nothing is missed that might later prove significant. But there's also acceptance that some questions simply can't be answered from remote observation alone. we'll know what we can know. We won't know everything. And we'll have to make peace with that uncertainty, as we do with so many aspects of astronomical observation where direct investigation remains beyond our technological capabilities. December 15th, 2025. A date that might become historical. The moment humanity observed its closest confirmed encounter with an interstellar visitor. Or a date that will be forgotten. Just another observation of just another comet that briefly caught attention before fading into the archival catalogues where thousands of other solar system objects are documented and largely ignored. Which it becomes depends entirely on what the data reveals. This is where the story pauses, not ends. The object continues its trajectory. The observations will proceed as planned. Analysis will eventually produce conclusions. But the narrative must pause here at the threshold of December, because what comes next depends on data we don't yet have. 3 Atlas might prove to be exactly what most astronomers expect. A large, unusual, but ultimately natural comet from another star system. The statistical improbabilities will be explained as coincidences that seem significant only because we were paying attention. The mass will be reconciled with composition through better models. The trajectory alignment will be filed as one of those unlikely but not impossible occurrences that happen occasionally in a large enough sample space. Or it might prove to be something that defies easy categorization. Not obviously artificial, it would take unambiguous evidence like geometric structures or radio transmissions to reach that conclusion, but strange enough that natural comet doesn't quite capture what we're observing. An object that raises more questions than it answers. That leaves researchers debating interpretation without reaching consensus. Or, with vanishingly small probability, it might prove to be something that forces us to reconsider our assumptions about what exists in our cosmic neighborhood. Something whose characteristics can't be explained through natural processes alone. Something that requires acknowledging the possibility, however uncomfortable, that we're not looking at debris from planetary formation, but at a product of intentional design we don't know. We can't know until December's observations are complete and analyzed, and even then, we might not know with certainty. Astronomical observation rarely provides absolute proof, only varying degrees of confidence in competing interpretations. What we can say is this: 3 Atlas represents an object unusual enough that careful investigation is warranted regardless of ultimate conclusions. Its mass, trajectory, timing, and chemistry place it at the boundary of what we consider ordinary, making it worth studying thoroughly to understand whether our models of interstellar objects need refinement. The December observations will provide the best data we're likely to obtain on this particular visitor. What we learn will shape how we approach future interstellar objects as they're discovered in increasing numbers over coming years. And somewhere in that data, in the images and spectra and measurements being gathered even now, lies information that will either reinforce our understanding of how the universe works or challenge it in ways we haven't anticipated. That's what December offers. Not certainty, but data. Not answers necessarily, but information that narrows the range of reasonable hypotheses. Not revelation, but the possibility of being surprised by what we find when we look carefully at something genuinely unfamiliar. The closest an interstellar visitor has come to Earth in recorded history. What it means depends entirely on what it is. And what it is depends on paying attention carefully enough to recognize the truth when the evidence reveals it. December will tell us what we need to know if we're watching closely enough to see it. The rest is just waiting. Chapter 21. The Hidden Mathematics of Cosmic Coincidence. Let's get our heads around the sheer improbability of what we're witnessing. When you break down the numbers, 3 Atlas isn't just unusual, it's a statistical unicorn that should make any rational person's jaw drop. First, let's talk about that trajectory alignment. The probability of any interstellar object aligning within 5 degrees of our ecliptic plane is roughly 1 in 500. That's already striking a cosmic lottery ticket. But then you add the planetary encounters and the odds skyrocket into astronomical territory. The Mars encounter alone had a probability of about 1 in 200,000. When you factor in both the spatial proximity and timing, Venus, another 1 in 50,000 shot, Jupiter's close approach, approximately 1 in 100,000. When you multiply these independent probabilities together, you're looking at odds of roughly 1 in 1 trillion that all 3 encounters would happen by pure chance during a single pass through our solar system. But wait, it gets wilder. The perihelion timing during solar conjunction adds another layer of improbability. The chance that an object would reach its closest point to the Sun precisely when Earth is positioned on the opposite side is about 1 in 25. When you factor this into our already staggering equation, you're now facing odds of approximately 1 in 25 trillion. Now let's throw in the mass anomaly. Based on our models of interstellar object populations, the probability of detecting a 5-kilometer object within just a decade of systematic searching is roughly 1 in 1,000. We should expect such massive visitors only once every 1,000 years or so, yet here we are with 1 in our observational lifetime. Multiply that into our equation, and we're now at odds of about 1 in 25 quadrillion. That's 25 with 15 zeros after it. To put that in perspective, if you bought a single lottery ticket with those odds, you'd be more likely to be struck by lightning twice in the same day, while simultaneously finding a pearl in every oyster you opened for breakfast. The chemistry adds yet another layer of statistical weirdness. The detection of nickel tetracarbonyl, a compound never observed in nature, only in industrial manufacturing, combined with the complete absence of iron, which should appear in roughly equal amounts, represents another statistical anomaly. The probability of this specific chemical signature occurring naturally is difficult to calculate precisely, but conservative estimates place it at no better than 1 in 10,000. When you incorporate the chemical anomaly into our already mind-boggling equation, you arrive at a combined probability of approximately 1 in 250 quadrillion that all these unusual characteristics would align in a single object through pure chance. Now here's where things get really interesting. In most scientific contexts, when you encounter probabilities this remote, you don't just dismiss them as coincidence. You start questioning whether your fundamental assumptions about the situation are correct. In particle physics, the standard for claiming discovery of a new particle is 5 sigma roughly, a 1 in 3.5 million probability that the observed effect is due to random chance. In genetics, researchers consider genome-wide associations significant when they reach a threshold of about 1 in 100,000. Yet here we are, facing probabilities orders of magnitude more extreme than these established scientific thresholds, and many in the astronomical community are still treating these anomalies as merely interesting coincidences. This isn't to say that 3 Atlas is definitely artificial. The natural explanation remains more probable given what we know about the abundance of natural versus technological objects in space. But the statistical profile of this object demands more than casual dismissal. It warrants the kind of rigorous investigation that would be automatic in any other scientific field facing such extreme improbabilities. The mathematics is telling us something important. Whether we're listening is another question entirely. Chapter 22. The Engineering Perspective. Let's step back and consider 3 Atlas from an engineering standpoint. If you were tasked with designing an interstellar probe capable of surveying star systems, what would it look like? How would it behave? First, you'd need to consider the immense timescales involved. Interstellar travel takes thousands or millions of years at feasible velocity. Your probe would need to survive this journey, which means protecting it from radiation, micrometeoroid impacts, and the gradual degradation of materials over millennia. The most logical approach? Disguise it as something natural. A probe that obviously looks artificial would attract attention, potentially from civilizations that might not be friendly. Better to make it appear as a common object that wouldn't warrant special scrutiny. The mass of 3 Atlas 33 billion tons makes perfect sense from this perspective. A hollow structure with walls a few hundred meters thick would provide radiation shielding, structural integrity, and internal space for instruments and power systems. The mass would also help the probe maintain its trajectory despite minor course corrections or external perturbations. The unusual chemistry, also explainable from an engineering standpoint. The nickel tetracarbonyl emission could be a byproduct of power systems or industrial processes within the probe. The absence of iron might indicate careful selection of materials to minimize detectable signatures or to optimize performance. The trajectory alignment with our ecliptic plane and the precise timing of planetary encounters suggests sophisticated navigation capabilities, and advanced civilization could easily calculate trajectories that would bring their probe close to multiple planets for observation, while minimizing the energy required for course corrections. The perihelion timing during solar conjunction is perhaps the most telling from an engineering perspective. If you wanted to make course corrections without being observed, doing so when your target civilization can't see you because of their star's glare is strategically brilliant. It's the cosmic equivalent of making your move when no one is looking. The lack of radio signals also makes sense. An advanced probe designed for discretion would likely use communication methods that are difficult to detect or distinguish from natural phenomena. It might communicate through gravitational waves, neutrinos, or quantum entanglement methods we might not even recognize as artificial. From this engineering perspective, 3 Atlas exhibits exactly the characteristics you'd expect from a technologically sophisticated probe designed to survey star systems while maintaining discretion. The question isn't whether these features could occur naturally, but whether they make more sense as the product of intentional design. This doesn't prove artificiality. Of course, nature is capable of producing complex and surprising phenomena. But when an object displays multiple characteristics that align perfectly with what you'd expect from engineered technology, it's worth considering that explanation with the same scientific rigor applied to natural hypotheses. The engineering perspective doesn't give us definitive answers, but it provides a framework for understanding why 3 Atlas looks the way it does and why its unusual characteristics might make more sense as design features rather than random coincidences. Chapter 23. The philosophical implications. Regardless of what 3 Atlas ultimately proves to be, its appearance forces us to confront some profound philosophical questions about our place in the cosmos and how we approach the unknown. The first question is about epistemology, how we know what we know. Our current scientific methodology is optimized for studying natural phenomena. We develop hypotheses based on natural processes, design experiments to test them, and refine our understanding through observation and analysis. But what happens when we encounter something that might not be natural? Our standard methods might not be adequate to recognize or understand it. We might dismiss anomalies as measurement errors or coincidences, simply because they don't fit within our existing frameworks. 3 Atlas challenges us to expand our epistemological toolkit. It asks us to consider how we would recognize artificiality if it doesn't conform to our expectations. It forces us to confront the limitations of our knowledge and the possibility that the universe might be more complex and varied than we currently imagine. The second question is about our relationship to the unknown. Throughout human history, we've tended to either romanticize or fear what we don't understand. We've either projected our hopes onto mysterious phenomena or reacted with suspicion and hostility. 3 Atlas offers an opportunity to develop a more nuanced approach to the unknown, one that balances curiosity with caution, that acknowledges possibilities without jumping to conclusions, that maintains scientific rigor while remaining open to extraordinary possibilities. The third question is about our responsibility as a species. If there is even a small chance that 3 Atlas represents evidence of extraterrestrial intelligence, what are our obligations? Do we have a responsibility to investigate thoroughly, to prepare for potential contact, to consider the implications for humanity's future? These questions extend beyond science into ethics, policy, and even theology. They force us to consider how we would respond to the discovery that we're not alone in the whole universe, a possibility that would fundamentally transform our understanding of ourselves and our place in the cosmos. The fourth question is about the nature of coincidence itself. We tend to think of coincidences as random events without deeper meaning, but mathematics teaches us that extreme improbabilities demand explanation. When multiple unlikely events cluster together, it's often a sign that there's something we're not seeing. 3 Atlas challenges us to reconsider our relationship to coincidence and statistical improbability. It asks us to recognize that sometimes the most unlikely explanation might be the correct one, even if it contradicts our assumptions about how the universe works. These philosophical implications extend far beyond a single interstellar object. They touch on fundamental questions about knowledge, reality, and our understanding of the cosmos. Regardless of what 3 Atlas ultimately proves to be, it has already served an important function by forcing us to confront these questions and expand our thinking about what might be possible in the vast expanse of space. Chapter 24. The cultural impact. Even if 3 Atlas proves to be entirely natural, its appearance has already had a significant cultural impact. It has captured public imagination in a way few astronomical phenomena have in recent years, inspiring art, music, literature, and philosophical reflection. The mystery surrounding 3 Atlas taps into something deep in the human, our fascination with the unknown and our longing to understand our place in the cosmos. This isn't a new phenomenon. Humans have been looking to the heavens and wondering about our relationship to the wider universe since we first gazed at the stars. What's different now is that we have the scientific tools and knowledge to investigate these questions in ways our ancestors could only dream of. We can analyze the composition of objects from other star systems, calculate their trajectories with precision, and gather data that helps us understand the universe in unprecedented detail. 3. Atlas represents a convergence of ancient wonder and modern capability, perfect storm of mystery and methodology that speaks to both our emotional and intellectual curiosity. It reminds us that even in our age of scientific advancement, there are still phenomena that challenge our understanding and inspire our imagination. The cultural impact extends beyond just inspiring wonder. 3 Atlas has also sparked important conversations about how we approach scientific investigation, how we communicate uncertainty to the public, and how we prepare for the possibility of revolutionary discoveries. These conversations matter because they shape how society relates to science and how science responds to society's questions and concerns. In an era of increasing scientific specialization and technical complexity, finding ways to bridge the gap between specialized knowledge and public understanding is more important than ever. 3. Atlas has also inspired a new generation of scientists and citizen researchers. The mystery surrounding the object has encouraged people to look up at the night sky with renewed curiosity, to learn more about astronomy and space science, and to participate in the collective human project of understanding our place in the cosmos. This cultural impact will endure regardless of what 3 Atlas ultimately proves to be. The object has already served as a catalyst for curiosity, conversation, and contemplation, functions that are valuable in themselves, regardless of the scientific outcome. In a world often divided by differences, the shared wonder inspired by 3 Atlas reminds us of our common humanity and our universal quest for knowledge and understanding. It connects us to each other and to the vast cosmos we all inhabit, reminding us that we're all part of something much larger than ourselves. Chapter 25. The technological imperative. Let's get real about what we're facing here. If 3 Atlas does turn out to be artificial, it represents a technological imperative that humanity cannot afford to ignore. The implications would be staggering, forcing us to confront our place in a universe where we're not the only intelligent species, capable of manipulating our environment on cosmic scales. First and foremost, confirmation of artificial origin would instantly resolve the Fermi paradox, the question of why we haven't detected evidence of extraterrestrial civilizations. despite the high probability of their existence? The answer would be simple. They're out there. A developed technology capable of traversing the vast distances between stars. This revelation would fundamentally transform our understanding of our place in the cosmos. We would go from being potentially alone to being part of a galactic community, or at least a galactic neighborhood with other technological residents. The psychological impact of such a discovery cannot be overstated. From a technological perspective, an artificial 3 Atlas would represent a treasure trove of information about advanced engineering. Even if we couldn't examine it directly, studying its characteristics would provide insights into propulsion systems, materials, science, energy generation, and spacecraft design that are centuries or millennia beyond our current capabilities. The strategic implications would be equally profound. If one civilization has developed interstellar probes, it's likely that others have as well. This would suggest that our solar system might be regularly visited by various probes, some of which we might have missed or misidentified as natural objects. This realization would create an urgent need to develop better methods for detecting and studying such objects. It would drive investment in astronomical infrastructure, space-based observation platforms, and perhaps even missions designed to intercept future interstellar visitors. The political implications cannot be ignored either. Confirmation of extraterrestrial technology would likely trigger a new space race. As nations compete to be the first to study or potentially communicate with such objects, it could also lead to new international frameworks for how humanity collectively responds to such discoveries. From a scientific perspective, an artificial 3 Atlas would revolutionize multiple fields. Astrophysics would need to incorporate the possibility of artificial objects into models of solar system dynamics. Chemistry would have to account for industrial processes occurring in interstellar space. Planetary science would need to consider the possibility of engineered objects among natural populations. Perhaps most importantly, confirmation of artificial origin would force us to confront existential questions about our future. If other civilizations have survived long enough to develop interstellar technology, it suggests that technological civilizations can overcome the challenges that threaten their existence. Nuclear war, climate change, asteroid impacts, and other existential risks. This would provide hope that humanity might also navigate these challenges and join the community of long-lived technological civilizations. It would suggest that our future among the stars is not just possible, but perhaps inevitable. If we make the right choices, the technological imperative, represented by an artificial 3 Atlas, would be both a challenge and an opportunity. It would challenge us to accelerate our own technological development, to overcome divisions that might prevent us from acting collectively, and to prepare for a future as part of a larger cosmic community. But it would also offer the opportunity to learn from more advanced civilizations, to benefit from their knowledge and experience, and perhaps to avoid some of the pitfalls they might have encountered on their own journeys through the cosmos. Whether 3 Atlas proves to be artificial or not, the possibility alone creates a technological imperative to develop better methods for studying interstellar objects and preparing for the day when we do encounter undeniable evidence of extraterrestrial technology. Chapter 26. The search for signatures. As December approaches, researchers are refining their search for what are called technosignatures, observable evidence that would indicate artificial origin. These go beyond the obvious geometric structures or radio signals that most people associate with evidence of extraterrestrial technology. One area of focus is the object's light curve, how its brightness changes over time. Natural objects typically show regular patterns of brightening and dimming based on rotation and surface reflectivity. Artificial objects might display anomalous patterns, such as sudden brightness changes not correlated with rotation, or periodic variations that suggest controlled orientation, rather than random tumbling dot. Another area is the object's thermal emission. Natural objects have thermal properties determined by their composition and rotation. Artificial objects might display unusual thermal characteristics, such as temperature distributions that don't match what would be expected from natural heating and cooling processes. The composition of outgassed materials provides another potential avenue for detecting artificiality. While 3 Atlas's chemical composition is unusual, certain patterns would be more indicative of artificial origin. For example, the presence of specific isotopic ratios that differ significantly from natural abundances, or the detection of manufactured compounds that couldn't form through natural processes. The object's trajectory offers yet another potential source of technology. While we've already noted the unusual alignment and timing, more subtle deviations from purely gravitational motion could indicate artificial propulsion or navigation systems. Even small course corrections that don't match what would be expected from natural outgassing could be significant. Researchers are also looking at the object's rotational characteristics. Natural objects typically rotate in ways that reflect their formation, history, and subsequent interactions. Artificial objects might display rotation patterns that suggest stabilization systems, controlled orientation, or other indicators of engineering. The shape of the coma and tail could potentially reveal technosignatures as well. While comets typically show fairly predictable patterns of gas and dust release, artificial objects might display unusual jet structures, asymmetries, or other features that suggest controlled rather than natural processes. Even the object's electromagnetic properties could provide clues. Natural objects have characteristic responses to solar, wind, and magnetic fields. Artificial objects might display anomalous electromagnetic interactions, such as unexpected magnetic signatures or unusual responses to solar radiation. What's particularly interesting about this search for technosignatures is that it's not just about looking for obvious evidence of artificiality. It's about recognizing subtle patterns that might indicate artificial origin, even when the object is designed to appear natural. This requires a sophisticated understanding of both natural processes and potential engineering solutions. It also requires careful analyses to distinguish between truly anomalous features and natural variations that might simply be unfamiliar to us. The challenge is compounded by the fact that we have only a limited sample of interstellar objects to compare against, with only 3 confirmed visitors to our solar system. Our understanding of what constitutes normal for these objects is still evolving. Despite these challenges, the search for technosignatures represents one of the most exciting frontiers in astronomy. It combines rigorous scientific methodology with imaginative speculation about what advanced technology might look like. Whether or not 3-Atlas displays any of these techno-signatories, developing the methods to search for them is valuable in itself. It prepares us for future discoveries and helps us refine our understanding of both natural and potential artificial phenomena in our cosmic neighborhood. Chapter 27. The Role of Citizen Science. One of the most inspiring aspects of the 3-Atlas story has been the involvement of citizen scientists, amateur astronomers, and enthusiasts who have contributed valuable observations and analysis to the scientific investigation. These citizen scientists have played several important roles in the study of 3-Atlas. Some have contributed observational data using personal telescopes and equipment, helping to fill gaps in professional observations and providing additional perspectives on the object's behavior. Others have participated in distributed computing projects, helping to analyze the massive amounts of data being collected by professional observatories. This collective processing power has accelerated the analysis of spectral data, trajectory calculations, and other computational aspects of the investigation. Perhaps most importantly, citizen scientists have brought fresh perspectives to the investigation, unconstrained by institutional orthodoxies or professional pressures. Some have asked questions or proposed explanations that might have been overlooked in more traditional scientific settings. This involvement of citizen science in the 3-Atlas investigation represents a broader trend in astronomy toward more open and collaborative approaches to research. Projects like Galaxy Zoo, Zooniverse, and various citizen astronomy initiatives have demonstrated the value of involving the public in scientific investigations. For 3-Atlas specifically, citizen science has helped address some of the observational gaps created by the limited availability of professional telescope time and the geographical distribution of major observatories. By creating a global network of amateur observers, researchers have been able to maintain more continuous monitoring of the object than would otherwise be possible. Citizen scientists have also played an important role in communicating the science to the broader public through blogs, social media, and community organizations. They've helped translate technical findings into accessible language and maintain public interest in the investigation. This public engagement is particularly valuable for a phenomenon like 3-Atlas, where the questions being investigated touch on fundamental aspects of our place in the cosmos. By involving more people in the process, we create broader public understanding of both the scientific method and the specific questions being investigated. The success of citizen science in the 3-Atlas investigation suggests models for future research on unusual astronomical phenomena. As professional observatories become increasingly oversubscribed, and as the volume of astronomical data continues to grow, creating effective partnerships between professional and citizen scientists will become increasingly important. This doesn't mean that citizen science replaces professional research. Rather, it creates a complementary relationship where each group contributes their strengths, professional scientists with their specialized knowledge and equipment, citizen scientists with their numbers, enthusiasm, and diverse perspectives. For 3-Atlas, this collaboration has already yielded valuable insights and will likely continue to do so as December's observations approach and as the subsequent analysis unfolds. It represents one of the most positive aspects of this investigation, the way it has brought people together in a collective quest for knowledge. Chapter 28. Preparing for December. As the critical December observation window approaches, researchers around the world are making final preparations for what will be the most intensive period of observation for 3 Atlas. These preparations involve coordinating telescope time, calibrating instruments, and developing protocols for rapid analysis of incoming data. One of the key challenges is ensuring that observations are coordinated across multiple facilities and wavelengths. Different telescopes and instruments have different capabilities, and maximizing the scientific return requires careful planning to ensure that each observation complements others rather than duplicating efforts. Another challenge is developing protocols for rapid analysis of incoming data. With the limited observation window, researchers need to be able to quickly identify any anomalies or unusual features that might warrant additional observation or different analytical approaches. Weather represents another concern. While space-based telescopes like Hubble and the James Webb Space Telescope aren't affected by Earth's weather, ground-based observatories are. Researchers are developing contingency plans to ensure that observations can continue even if some facilities are hampered by poor weather conditions. Data management is yet another consideration. The December observations will generate massive amounts of data that need to be stored, processed, and distributed to research teams around the world. This requires robust computational infrastructure and efficient data transfer protocols. Perhaps most importantly, researchers are preparing themselves mentally and scientifically for the range of possible outcomes. The observations might confirm that 3 Atlas is a natural object. They might reveal anomalies that deepen the mystery, or they might provide evidence that points toward artificial origin. Each of these outcomes requires different analytical approaches and has different implications for future research. By preparing for all possibilities, researchers ensure that they'll be ready to follow up quickly on whatever December's observations reveal. The preparations also involve international coordination, with observatories around the world participating in the observation campaign. Ensuring that data is shared efficiently and that analysis efforts are not duplicated requires careful planning and international communication. This international aspect of the preparation reflects the global nature of the 3 Atlas investigation. Regardless of what the object proves to be, it belongs to all humanity. And understanding it is a collective endeavor that transcends national boundaries. As December approaches, there's a sense of anticipation in the scientific community. Whatever the observations reveal, they will represent the culmination of months of preparation and years of anticipation. The data gathered during this critical window will shape our understanding of 3 Atlas and our approach to future interstellar objects for years to come. The preparations themselves represent something valuable, a demonstration of how the global scientific community can come together to address a compelling question, combining resources, expertise, and enthusiasm in a collective quest for knowledge. This spirit of collaboration and curiosity is perhaps the most important preparation of all, ensuring that whatever descent brings, we'll be ready to learn from it and to incorporate those lessons into our ongoing exploration of the cosmos. Chapter 29. The historical context. To truly appreciate the significance of 3 Atlas, we need to understand how it fits into the broader history of human encounters with the unknown. Throughout recorded history, there have been moments when humanity confronted phenomena that challenged our understanding of the world and our place in it. In ancient times, these encounters often took the form of comets, eclipses, and other celestial events that were interpreted as omens or messages from the gods. The appearance of Halley's Comet in 1066, for example, was seen as an omen that influenced the outcome of the Battle of Hastings. The Great Comet of 1577 was observed by Tycho Brahe, whose measurements helped demonstrate that comets were atmospheric phenomena rather than objects within Earth's atmosphere. The invention of the telescope in the early 17th century opened new windows on the cosmos, revealing phenomena that challenged the geocentric model of the universe. Galileo's observations of the moons of Jupiter, the phases of Venus, and the mountains on the moon provided evidence that supported the heliocentric model proposed by Copernicus. In the 19th century, the discovery of Neptune through mathematical prediction rather than direct observation demonstrated the power of scientific reasoning to reveal hidden aspects of our solar system. The detection of canals on Mars by Percival Lowell, though later proven to be optical illusions, sparked public imagination about the possibility of extraterrestrial life. The 20th century brought even more profound discoveries. Edwin Hubble's observations of distant galaxies revealed that the universe was expanding, fundamentally changing our understanding of cosmic origins. The detection of the cosmic microwave background radiation provided evidence for the Big Bang theory. The discovery of exoplanets beginning in the 1990s confirmed that planets orbit other stars, suggesting that Earth might not be unique. Each of these discoveries forced humanity to revise our understanding of the cosmos and our place within it. Each represented a moment when the unknown became known, when mystery gave way to understanding. 3 Atlas represents the latest chapter in this ongoing story of cosmic discovery. Like previous encounters with the unknown, it challenges our assumptions and pushes the boundaries of our knowledge. But unlike previous discoveries, it carries the potential to reveal not just new aspects of natural phenomena, but evidence of intelligence beyond Earth. This historical context helps us understand why 3 Atlas captures our imagination so powerfully. It taps into the same human impulse that drove our ancestors to watch the skies and wonder about their meaning. It represents the continuation of a quest for knowledge that has defined human civilization since its earliest days. What's different now is the sophistication of our tools and the depth of our understanding. We no longer interpret celestial events as omens or messages from gods. Instead, we apply the scientific method to systematically investigate and understand these phenomena. But the fundamental wonder remains the same. We still look to the heavens. With curiosity and awe, still seek to understand our place in the cosmos. Still wonder whether we're alone in the vast expanse of space. 3 Atlas speaks to this enduring aspect of human nature. It reminds us that despite all our scientific advances, there are still mysteries to be solved, still questions to be answered, still wonders to be discovered. It connects us to the long lineage of humans who have looked up at the night sky and felt that sense of cosmic wonder. Chapter 30. The Psychological Dimension. The appearance of 3 Atlas has triggered a range of psychological responses that tell us as much about human nature as they do about the object itself. Understanding. These responses helps us appreciate why this particular interstellar visitor has captured our imagination so powerfully. Another psychological response has been what's known as confirmation bias. Our tendency to interpret new information in ways that confirm our existing beliefs. People who already believe in extraterrestrial intelligence are more likely to see 3 Atlas as potential evidence of that belief, while skeptics are more likely to interpret the same data as supporting natural explanations. This psychological dimension helps explain why there's such divergence in how people interpret the same information about 3 Atlas. It's not just about the data itself. It's about the mental frameworks through which we process that data. The appearance of 3 Atlas has also triggered what psychologists call existential curiosity, our desire to understand fundamental questions about our existence and place in the cosmos. This is a deeper and more profound form of curiosity than simple interest in facts or figures. It's the kind of curiosity that drives philosophical inquiry and scientific exploration. This existential curiosity explains why 3 Atlas has resonated so strongly with people beyond the scientific community. It's not just an interesting astronomical phenomena, it's a catalyst for contemplating some of the most fundamental questions human beings can ask. Are we alone? What is our purpose? What is our future? The object has also triggered what might be called cosmic humility, a recognition of how small we are in the vast expanse of space and time. This feeling can be uncomfortable, but it can also be liberating, helping us put our earthly concerns into perspective and appreciate the preciousness of our existence. For some, 3 Atlas has triggered anxiety or fear, particularly those who worry about the potential implications of encountering a more advanced civilization. This response is rooted in what psychologists call the stranger danger instinct, our evolved wariness of unknown entities that might pose a threat. Others have experienced what might be called cosmic optimism, a hopeful excitement about the possibility that we might not be alone and that our future among the stars might be richer and more interesting than our present existence on Earth. These varied psychological responses to 3 Atlas reflect the complexity of human nature and the different ways we process information that challenges our understanding of the world. They remind us that scientific discoveries don't exist in a vacuum. They're interpreted through the lens of human psychology, culture, and experience. Understanding these psychological dimensions doesn't diminish the scientific significance of 3 Atlas. Instead, it enriches our appreciation of why this particular object has captured our imagination so powerfully and why it matters to so many people beyond the scientific community. It also reminds us that the search for knowledge about the cosmos is not just an intellectual exercise. It's an emotional and existential journey that touches on some of the deepest aspects of what it means to be human. Chapter 31. The Media Landscape. The way 3 Atlas has been covered in the media provides fascinating insights into how modern society processes and communicates scientific discoveries, especially those with potentially profound implications. Traditional media outlets have generally taken a cautious approach to 3 Atlas, framing it as an unusual but natural astronomical phenomenon. Headlines have typically emphasized the object's size and trajectory while downplaying the more speculative aspects of the investigation. This reflects journalistic norms that prioritize accuracy and avoid sensationalism. Specialized science media has provided more detailed coverage, exploring the technical aspects of the investigation and the various hypotheses being considered. These outlets have generally maintained a balanced perspective, giving appropriate weight to both natural and artificial explanations. While emphasizing the uncertainty that still exists, social media has presented a more diverse and often more speculative landscape. Here, theories about 3 Atlas range from the scientifically grounded to the wildly imaginative. Some users have engaged in serious discussion of the evidence, while others have propagated conspiracy theories or unfounded claims. This diversity of coverage reflects both the strengths and weaknesses of our modern media ecosystem. On one hand, it provides multiple perspectives and allows for nuanced discussion of complex topics. On the other hand, it can be difficult for non-experts to distinguish between credible information and speculation. One interesting aspect of the media coverage has been how it has evolved over time. Initially, most coverage treated 3 Atlas as a straightforward astronomical discovery. As more unusual characteristics emerged, coverage began to acknowledge the possibility of artificial origin. Though typically with appropriate caveats, the media landscape has also influenced how the scientific investigation itself has proceeded. The intense public interest has created pressure on researchers to communicate their findings clearly while avoiding premature speculation. It has also highlighted the need for better communication strategies when dealing with potentially revolutionary discoveries. Perhaps most importantly, the media coverage of 3 Atlas has demonstrated the enduring public fascination with space and the possibility of extraterrestrial life. Even in an era of information overload and competing priorities, stories about 3 Atlas have consistently generated significant engagement and discussion. This public interest is valuable because it creates support for scientific research and helps ensure that discoveries like 3 Atlas receive the attention and resources they deserve. It also reflects the human desire to understand our place in the cosmos and to explore the unknown. The media coverage of 3 Atlas also highlights the challenges of communicating uncertainty in a culture that often seeks definitive answers. Science is a process of gradually reducing uncertainty, not of arriving at absolute certainty. Communicating this nuanced reality while maintaining public interest is an ongoing challenge. As December's observations approach, the media landscape will likely become even more focused on 3 Atlas. How this coverage unfolds will influence public understanding of the investigation and its implications, regardless of what the observations ultimately reveal. The media coverage of 3 Atlas represents a case study in how modern society processes and communicates scientific discoveries that challenge our understanding of the world. It reflects both the promise and the peril of our information-rich age, where diverse perspectives compete for attention in a complex and rapidly evolving media. Ecosystem. Chapter 32. The educational opportunity. Regardless of what 3 Atlas ultimately proves to be, its appearance has created a tremendous educational opportunity. that can help inspire the next generation of scientists and inform the public about the nature of scientific investigation. One of the most valuable aspects of this educational opportunity is how it demonstrates the scientific method in action. Rather than presenting science as a collection of established facts, the investigation of 3 Atlas shows science as a process of asking questions, gathering evidence, testing hypotheses, and gradually refining our understanding. This process-oriented view of science is particularly valuable because it helps people understand how scientists deal with uncertainty and how conclusions are reached through careful analysis of evidence rather than through sudden revelation or authority. 3 Atlas also provides an opportunity to teach about specific scientific concepts and methods. Spectroscopy, orbital mechanics, statistical analysis, and many other scientific tools and techniques are being applied to understand this object, making it a perfect case study for teaching these concepts. The interdisciplinary nature of the AE investigation is another valuable educational aspect. Understanding 3 Atlas requires knowledge from astronomy, physics, chemistry, engineering, statistics, and even philosophy. This demonstrates how different fields of knowledge can work together to address complex questions for educators. 3 Atlas offers a way to make abstract scientific concepts concrete and engaging. Rather than learning about spectroscopy or orbital mechanics in isolation, students can see how these tools are applied to investigate a real and compelling mystery. The object also provides an opportunity to teach about critical thinking and scientific literacy. By examining the evidence and considering different hypotheses, students can learn how to evaluate claims, distinguish between speculation and evidence, and understand the nature of scientific uncertainty. Perhaps most importantly, 3 Atlas can help inspire curiosity and wonder about the universe. In an era when many students are disengaged from science, the mystery surrounding this object offers a way to spark interest and encourage further exploration. This educational opportunity extends beyond formal education settings. Museums, science centers, and other informal educational institutions can use 3 Atlas to create exhibits and programs that engage the public in science and space exploration. Online platforms offer yet another avenue for educational outreach. Virtual lectures, interactive simulations, and citizen science projects can help people around the world learn about 3 Atlas and participate in the investigation. The educational value of 3 Atlas will endure regardless of what the object ultimately proves to be, even if it turns out to be a natural object. The investigation process itself provides valuable insights into how science works and how we expand our understanding of the universe. Chapter 33. The technological ripple effect. The investigation of 3 Atlas has already sparked technological innovations that extend far beyond the immediate study of this particular object. When humanity faces a compelling scientific challenge, we often develop new tools and methods that have applications far beyond the original problem. One area of innovation has been in telescope technology. The need to gather detailed observations of 3 Atlas has accelerated the development of more sensitive detectors, improved adaptive optics systems for ground-based telescopes, and more sophisticated data processing algorithms. These improvements will benefit all areas of astronomical research, not just the study of interstellar objects. Data analysis techniques have also advanced significantly. The massive amounts of data being collected on 3 Atlas require new approaches to storage, processing, and analysis. Machine learning algorithms have been developed to automatically identify anomalies in spectral data. Trajectory calculations have been refined to handle more complex scenarios, and new visualization tools have been created to help interpret multidimensional datasets. International collaboration has been enhanced through the development of better platforms for sharing data and coordinating observations. These platforms allow researchers around the world to access data from multiple observatories, contribute their own observations, and participate in collaborative analysis regardless of their location. Citizen science tools have also improved. The 3 Atlas investigation has inspired the development of new apps and platforms that allow amateur astronomers to contribute observations and participate in data analysis. These tools make it easier for non-professionals to make meaningful contributions to scientific research. Communication technologies have advanced as well. The need to coordinate observations across multiple facilities and share results quickly has led to improvements in real-time data transmission and collaborative platforms. These improvements will benefit many areas of scientific research that require rapid communication and coordination. Perhaps most importantly, the 3 Atlas investigation has stimulated thinking about new approaches to studying interstellar objects. Researchers have proposed dedicated telescope arrays specifically designed to detect and track these objects. Space-based observatories optimized for studying visitors from other star systems, and even missions designed to intercept future interstellar objects. These technological ripple effects demonstrate an important aspect of scientific discovery. The process of investigating compelling questions often leads to innovations that have applications far beyond the original problem. The tools and methods developed to study 3 Atlas will benefit many areas of science and technology for years to come. This technological dimension of the 3 Atlas story reminds us that scientific exploration drives innovation in ways that are often unpredictable but consistently valuable. By pushing the boundaries of what we can observe and understand, we develop new capabilities that enhance our ability to address a wide range of challenges. The technological ripple effects also highlight the interconnected nature of scientific progress. Advances in one area often enable progress in others, creating a virtuous cycle of innovation that accelerates our collective ability to understand and shape the world around us. As December's observations approach, we can expect further technological innovations as researchers deploy new tools and methods to gather the best possible data. These innovations will add to the technological legacy of 3 Atlas, ensuring that whatever we learn about the object itself, the investigation will have lasting value for science and technology. Chapter 34. The philosophical implications of detection. The possibility of detecting evidence of extraterrestrial technology through the investigation of 3 Atlas raises profound philosophical questions that extend far beyond the scientific details of the object itself. These questions touch on fundamental aspects of how we understand ourselves, our place in the cosmos, and the nature of knowledge itself. One of the most immediate philosophical questions concerns the nature of evidence. What would constitute sufficient evidence to conclude that 3 Atlas is artificial. How do we distinguish between genuine anomalies and coincidences? How do we deal with uncertainty when the implications of a conclusion would be so profound? These epistemological questions are particularly challenging because they force us to confront the limits of our knowledge and the criteria we use for drawing conclusions. In everyday life, we typically make decisions based on incomplete information, but the stakes involved with potential evidence of extraterrestrial technology raise the bar for what constitutes sufficient evidence. Another philosophical question concerns the nature of intelligence itself. If 3 Atlas is artificial, what would it tell us about the nature of the intelligence that created it? Would it suggest that intelligence follows similar evolutionary paths throughout the universe, or that there are multiple paths to technological capability? The question of consciousness also arises. Would an artificial interstellar probe necessarily imply conscious creators? Or could it be the product of a civilization that had developed advanced artificial intelligence without achieving consciousness in the way we understand it? The ethical implications are equally profound. If we detected evidence of extraterrestrial technology, what would be our ethical obligations? Would we have a responsibility to attempt communication? Would we need to consider the potential impact on the creators of the technology? How would we balance curiosity with caution? The question of meaning also comes into play. How would the discovery of extraterrestrial technology affect our understanding of human purpose and significance? Would it diminish our sense of specialness in the cosmos, or would it suggest that intelligence and technology are universal aspects of cosmic evolution? The philosophical implications extend to questions about the future of humanity. Would the discovery of extraterrestrial technology accelerate our own technological development? Would it inspire new philosophical and religious movements? Would it change how we approach global challenges and international cooperation? These philosophical questions don't have easy answers, but they're worth contemplating regardless of what 3 Atlas ultimately proves to be. The process of considering these questions helps us clarify our values and priorities, and it prepares us for a future in which we might not be alone in the universe. The philosophical dimension of the 3 Atlas investigation reminds us that science doesn't exist in isolation from broader questions about meaning, purpose, and value. The pursuit of knowledge is always intertwined with our understanding of ourselves and our place in the cosmos. By engaging with these philosophical questions, we enrich the scientific investigation and ensure that whatever we learn about 3 Atlas, we also learn something about ourselves and our relationship to the wider universe. Chapter 35. The Cultural Ripple Effect. Beyond the scientific and technological dimensions, the appearance of 3 Atlas has created cultural ripples that reflect and shape how we think about our place in the cosmos. These cultural impacts span art, literature, music, film, and other forms of creative expression. In the visual arts, 3 Atlas has inspired a new wave of cosmic-themed work. Painters, sculptors, and digital artists have created pieces that explore the mystery and beauty of interstellar objects, often blending scientific accuracy with imaginative speculation about what these objects might represent. Literature has seen a similar surge of interest. Science fiction writers have incorporated elements of the 3 Atlas story into their work, exploring various scenarios of what might happen if the object proved to be artificial. Literary fiction has also addressed the philosophical and existential questions raised by the investigation. Music has been another area of creative response. Composers have created pieces inspired by the journey of 3 Atlas through our solar system, often using unusual scales and harmonies to evoke the sense of cosmic mystery surrounding the object. Some musicians have even incorporated actual data from the investigation into their compositions. Film and television have also been influenced by 3 Atlas. Documentary makers have produced films exploring the scientific investigation and its implications, while fictional works have used the object as a jumping-off point for stories about contact with extraterrestrial intelligence. These cultural responses to 3 Atlas serve several important functions. They help process the emotional and existential impact of potentially revolutionary discoveries. They communicate complex scientific ideas to broader audiences. They inspire curiosity and wonder about the cosmos. Perhaps most importantly, they reflect the human impulse to make meaning out of mystery. When confronted with something that challenges our understanding, we turn to art and storytelling to help us process the implications and integrate them into our worldview. The cultural impact of 3 Atlas also extends to how we think about space exploration more broadly. The object has reignited public interest in space and inspired a new generation of space enthusiasts. This cultural shift could have important implications for future space missions and public support for space exploration. The cultural ripple effects of 3 Atlas demonstrate how scientific discoveries can influence society in ways that extend far beyond the scientific community. They show that our relationship to the cosmos is not just about technical understanding, but also about meaning, beauty, and inspiration. As December's observations approach, we can expect further cultural responses to the mystery of 3 Atlas. Whatever the observations reveal, these creative expressions will enrich our understanding of the object's significance and help us integrate its lessons into our cultural worldview. The cultural dimension of the 3 Atlas story reminds us that science and art are complementary ways of understanding the world. Both seek to reveal truths about reality, but they do so through different methods and speak to different aspects of human experience. Together, they create a more complete picture of our relationship to the cosmos and our place within it, ensuring that the legacy of 3 Atlas includes not just scientific knowledge, but also cultural enrichment and inspiration. Chapter 36. The Global Perspective. The investigation of 3 Atlas has demonstrated the power of international scientific cooperation. At a time when global collaboration is more important than ever, researchers from around the world have contributed observations, analysis, and insights to understand this mysterious visitor from another star system. This global cooperation takes many forms. Observatories in different countries have coordinated their observations to ensure continuous monitoring of the object. Research teams across continents have shared data and analytical techniques. Scientists have collaborated on papers and presentations that combine expertise from multiple institutions and national backgrounds. The international nature of the investigation reflects the reality that astronomy has always been a global endeavor. The cosmos doesn't respect national boundaries, and understanding it requires cooperation that transcends political differences. 3 Atlas has reinforced this fundamental aspect of astronomical research. What's particularly notable about the 3 Atlas investigation is how it has brought together researchers from countries that might have political tensions in other domains. In the pursuit of understanding this interstellar visitor, scientists have found common ground that transcends geopolitical divisions. This global cooperation has practical benefits as well. By combining observations from telescopes in both hemispheres, researchers can maintain continuous monitoring of the object as it moves across the sky. By pooling data from different instruments with various capabilities, they can build a more complete picture of the object's characteristics. The international nature of the investigation also brings diverse perspectives to bear on the problem. Scientists from different countries and cultural backgrounds sometimes approach questions in different ways, leading to insights that might not emerge from a more homogeneous group of researchers. The global cooperation around 3 Atlas serves as a model for how humanity might approach other collective challenges that transcend national boundaries. Climate change, pandemic response, and sustainable development all require the kind of international cooperation that the 3 Atlas investigation demonstrates. As December's observations approach, this global cooperation will become even more important, coordinating observations across multiple facilities, sharing data rapidly, and analyzing results collectively will require effective international collaboration at a scale that few scientific investigations have achieved. The global dimension of the 3 Atlases investigation also highlights the universal human fascination with the cosmos. Regardless of cultural background or national origin, people around the world are captivated by the mystery of this interstellar visitor and what it might represent. This shared wonder creates a foundation for international cooperation that extends beyond the scientific community. It reminds us that despite our differences, we all share the same planet and the same cosmic neighborhood, giving us common interests and common questions. The global perspective on 3 Atlas reminds us that the pursuit of knowledge is a fundamentally human endeavor that transcends political and cultural divisions. By working together to understand this mysterious visitor from another star system, we demonstrate the best aspects of our collective nature and our capacity for cooperation in the face of mystery and uncertainty. Chapter 37: The Economic Dimension. While much of the focus on 3 Atlas has been scientific and philosophical, the investigation has also had significant economic implications that are worth considering. These economic dimensions range from direct funding for research to indirect effects on technology, development, and commercial opportunities. The most direct economic impact has been the funding allocated to studying 3 Atlas's government agencies. Private foundations and research institutions have invested millions of dollars in telescope time, personnel, and analytical resources. This funding has supported jobs for astronomers, technicians, data analysts, and many other professionals involved in the investigation. This research funding has multiplier effects in the economy. The salaries paid to researchers and support staff circulate through local economies, supporting businesses and creating additional economic activity. The purchase of equipment and services for the investigation generates revenue for companies that supply these products and services. The technological innovations spurred by the 3 Atlas investigation also have economic implications. New telescope technologies, data analysis methods, and collaboration platforms developed for studying the object have commercial applications in other industries. These innovations can lead to new products, services, and even new companies. Space-related industries have also benefited from the increased public interest in 3 Atlas. Companies involved in space tourism, satellite services, and space-based observation have seen heightened interest in their offerings. The object has helped maintain public enthusiasm for space exploration, which supports the business case for commercial space ventures. The media and entertainment industries have capitalized on the 3 Atlas story as well. Documentaries, news coverage, and fictional works based on the object have generated revenue and created jobs in these sectors. The public fascination with the mystery has created marketable content across multiple platforms. Educational institutions have also benefited economically from the 3 Atlas investigation. Universities and research centers involved in the study have enhanced their reputations, attracting students, grants, and partnerships. The object has created opportunities for educational programs and courses focused on interstellar objects and related topics. The economic implications extend to future planning as well. The investigation of 3 Atlas has highlighted the value of developing capabilities for studying future interstellar objects. This has led to discussions about funding dedicated observatories, space missions, and research programs focused on these visitors from other star systems. There are also potential economic risks to consider. If 3 Atlas were to be confirmed as artificial, it could create economic disruptions as societies adjust to the implications of such a discovery. Markets might react unpredictably to such news, and industries might need to adapt to a new understanding of our place in the cosmos. The economic dimension of the 3 Atlas's investigation reminds us that scientific research is not just an intellectual pursuit, but also an economic activity with far-reaching implications. The funding, innovations, and commercial opportunities generated by the investigation demonstrate how curiosity-driven research can create economic value. As December's observations approach, we can expect further economic activity related to 3 Atlas. Media coverage will intensify, educational programs will expand, and discussions about future research capabilities will continue. Whatever the observations reveal, the economic impact of the investigation will extend beyond the immediate scientific results. The economic story of 3 Atlas highlights the interconnected nature of scientific research, technological innovation, and economic activity. By investing in understanding this mysterious visitor from another star system, we're not just expanding our knowledge of the cosmos, but also creating economic value that benefits society in multiple ways. Chapter 38. The Political Implications. The investigation of 3 Atlas has political dimensions that reflect and influence how societies organize themselves to address complex scientific questions. These political implications range from international cooperation to domestic policy decisions about research funding and priorities. One of the most significant political aspects of the 3 Atlas investigation has been the international cooperation. It has inspired, in an era of increasing geopolitical tension, the shared scientific interest in this interstellar object has created a foundation for collaboration that transcends political differences. This cooperation demonstrates how science can serve as a bridge between nations even when other relationships are strained. The investigation has also highlighted questions about research funding and priorities, the resources allocated to studying. 3 Atlas represent policy decisions about what kinds of scientific research deserve public support. These decisions involve political considerations about how to balance competing research needs and limited resources domestically. The 3 Atlas investigation has created opportunities for political leadership. Politicians who support space research and scientific exploration can point to the investigation as an example of valuable scientific work that deserves funding and attention. This can help build public support for science policies and research investments. The object has also raised questions about preparedness and planning. If 3 Atlas were to be confirmed as artificial, what would be the appropriate governmental response? Which agencies would take the lead? How would information be communicated to the public? These questions require policy, planning, and coordination. Across multiple levels of government, the international dimension of the investigation has also raised questions about governance. If we do encounter evidence of extraterrestrial intelligence, what international frameworks would guide our response? How would different countries coordinate their actions? Who would speak for humanity in potential communications? These questions don't have easy answers, but the 3 Atlas investigation has highlighted the need to consider them before we're faced with definitive evidence rather than after. The political implications of potential contact with extraterrestrial intelligence are too significant to leave to ad hoc decision-making. The investigation has also created political opportunities for education and public engagement. Politicians can use the public interest in 3 Atlas to promote science, education, and literacy. The object serves as a real-world example of why scientific research matters and why it deserves public support. As December's observations approach, the political implications of 3 Atlas will likely become more prominent. Whatever the observations reveal, there will be political decisions to make about follow-up research, communication strategies, and future preparedness. The political dimension of the 3 Atlas investigation reminds us that science doesn't exist in a political vacuum. Research priorities, funding decisions, and international cooperation all involve political considerations and policy choices. By understanding these political dimensions, we can better support the scientific investigation and its implications. The political story of 3 Atlas highlights the importance of thoughtful policy and international cooperation in addressing complex scientific questions. It demonstrates how shared scientific interests can create opportunities for collaboration even in a politically divided world. And it reminds us of the need to plan carefully for the implications of potentially revolutionary discoveries. Chapter 39. The religious and spiritual dimensions. The appearance of 3 Atlas has sparked discussions in religious and spiritual communities about how the potential discovery of extraterrestrial technology might fit into various belief systems. These discussions reflect the profound impact that such a discovery would have on how we understand our place in the cosmos and our relationship to the divine. Many religious traditions have long contemplated the possibility of life beyond Earth. The 3 Atlas investigation has given these contemplations new urgency and relevance. Religious leaders and scholars have engaged in dialogue about how their traditions would interpret evidence of extraterrestrial intelligence. Some religious perspectives see no conflict between their beliefs and the possibility of extraterrestrial technology. They view a universe filled with diverse life and intelligence as consistent with a creative divine force whose works are as vast and varied as the cosmos itself. Other religious traditions have approached the question more cautiously, concerned about how evidence of extraterrestrial intelligence might fit with specific theological doctrines or scriptural interpretations. These traditions are engaged in thoughtful consideration of how to integrate potential new discoveries into their existing frameworks. Spiritual but not religious perspectives have also found relevance in the 3 Atlas investigation. Many spiritual practices emphasize the interconnectedness of all things and the unity of the cosmos. The possibility that we might not be alone in the universe resonates with these perspectives and reinforces their sense of cosmic connection. The investigation has also sparked discussions about the nature of consciousness and whether it might take different forms throughout the universe. These discussions touch on deep questions about the relationship between mind and matter, between the physical and spiritual aspects of existence. Some religious and spiritual communities have viewed 3 Atlas through an eschatological lens, wondering whether the object might be related to end times prophecies or divine intervention. These interpretations vary widely but reflect the human tendency to seek meaning and purpose in unusual celestial events. The 3 Atlas investigation has also created opportunities for interfaith dialogue. Different religious traditions are engaging in conversation about how they would respond to evidence of extraterrestrial intelligence, finding common ground in their contemplation of humanity's place in the cosmos. These religious and spiritual dimensions of the 3 Atlas story remind us that scientific discoveries don't exist in isolation from our broader understanding of meaning and purpose. How we interpret potential evidence of extraterrestrial technology will be influenced by our existing beliefs and WORLDVI-EWS. As December's observations approach, religious and spiritual communities will be watching with interest, ready to interpret whatever results emerge through their particular lenses of meaning and understanding. Whatever the observations reveal, these interpretations will enrich our collective conversation about the implications of the discovery. The religious and spiritual dimensions of 3 Atlas highlight the complex interplay between scientific knowledge and belief systems. They remind us that how we understand the cosmos involves not just factual knowledge, but also questions of meaning, purpose, and our relationship to that which transcends the material world. Chapter 40. Preparing for all possibilities. As the critical December observation window approaches, researchers and policymakers are preparing for the range of possible outcomes and their implications. This preparation involves not just scientific planning, but also consideration of how to respond to and communicate whatever December's observations reveal. One aspect of this preparation is developing protocols for analyzing and verifying results. Given the potential significance of any evidence regarding the nature of 3 Atlas, researchers are establishing rigorous procedures to ensure that conclusions are based on solid evidence and thorough analysis. Communication strategies are another important aspect of the preparation. Regardless of what December's observations reveal, effective communication will be essential for helping the public understand the results and their implications. This involves preparing clear explanations, visualizations, and responses to potential questions. International coordination is also part of the preparation. Researchers around the world are establishing agreements about how to share and analyze data, how to coordinate announcements of results, and how to collaborate on follow-up investigations. This international cooperation will be essential regardless of what the observations reveal. Scenario planning is another key preparation strategy. Researchers and policymakers are considering various possible outcomes and developing response plans for each scenario. This approach helps ensure that whatever December reveals will be prepared to respond thoughtfully and effectively. Educational preparation is also underway. Teachers, professors, and science communicators are developing materials to help explain the December observations and their implications. These educational resources will help ensure that the public has access to accurate information and thoughtful analysis. Ethical considerations are part of the preparation as well. If December's observations were to provide evidence of artificial origin, there would be complex ethical questions to address. Preparing for these questions in advance helps ensure that we can respond thoughtfully rather than reactively. Media preparation is another important aspect. Journalists and science communicators are being briefed on what to expect from December's observations and how to interpret the results. This preparation helps ensure accurate and responsible media coverage of whatever emerges. Perhaps most importantly, psychological preparation is part of the process. The researchers involved in the December observations are preparing themselves, mentally and emotionally, for the range of possible outcomes. This psychological preparation helps ensure that they can analyze and interpret results with appropriate scientific rigor, regardless of what they reveal. This comprehensive preparation reflects the significance of the December observations and the potential implications of their results. By preparing for all possibilities, we ensure that whatever December reveals will be ready to respond thoughtfully, responsibly, and effectively. The preparation process itself has value beyond the immediate investigation of 3 Atlas. It establishes protocols and procedures that can be applied to future unusual astronomical discoveries. It strengthens international scientific cooperation and communication. It enhances our collective capacity for dealing with potentially revolutionary discoveries as December approaches. This preparation continues with researchers, policymakers, communicators, and educators all working to ensure that we're ready for whatever the observations reveal. This preparation represents the best of human foresight and planning, ensuring that we can make the most of this unique opportunity to expand our understanding of the cosmos. Chapter 41. The Technology of Detection. As we gear up for December's big show, let's talk about the incredible tech that's making this investigation possible. We're not just pointing some fancy binoculars at the sky, we're deploying an arsenal of cutting-edge instruments that represent the pinnacle of human observational capability. First up, the James Webb Space Telescope, the rock star of space observatories. With its 6.5-meter gold-plated mirror and infrared sensors that can detect heat from a bumblebee at the distance of the moon. Webb is giving us unprecedented thermal data on 3 Atlas. It's mapping temperature variations across the object's surface with precision that would have been unthinkable just a decade ago. Then there's Hubble, the old reliable that just keeps on giving. Despite being in service since 1990, Hubble's instruments have been upgraded multiple times, and it's still delivering high-resolution, visible and ultraviolet images that ground-based telescopes simply can't match because of atmospheric interference. Speaking of ground-based telescopes, the Very Large Telescope Array in Chile is bringing its 4 8.2-meter mirrors to bear on 3 Atlas, with adaptive optics that can correct for atmospheric turbulence in real time. VLT is capturing images sharp enough to resolve details as small as a few hundred meters across on the object's surface. The Gemini South Telescope, also in Chile, is contributing spectroscopic data that's revealing the chemical composition of 3 Atlases outgassing with incredible precision. Its multi-object spectrograph can simultaneously analyze light from different parts of the object, giving us a detailed chemical map. But here's where it gets really interesting. The European Space Agency's JUICE spacecraft, currently on its way to Jupiter, is positioned perfectly to observe 3 Atlas from a unique vantage point in space. Its suite of instruments was designed to study Jupiter's moons, but they're being repurposed to gather data on our interstellar visitor, NASA's Juno spacecraft. Orbiting Jupiter might also get in on the action when 3 Atlas passes by in March 2026. While that's after the December window, it could provide our last chance to gather high-quality data before the object becomes too faint to study effectively. On the ground, radio telescopes like the Green Bank Telescope in West Virginia and the Parkes Telescope in Australia are listening for any signals that might indicate artificial origin. While no systematic radio monitoring program has been officially announced, researchers are using observation time to check for any unusual emissions. The Mars Reconnaissance Orbiter's high-risk camera has already provided unique perspectives on 3 Atlas during its close approach to Mars. While the resolution was limited by the vast distance, these observations represent the first time we've imaged an interstellar object from another planet. What's particularly cool about this technological arsenal is how it's being coordinated. Researchers have developed sophisticated scheduling algorithms to ensure that each telescope is observing at the optimal time and that observations from different facilities complement rather than duplicate each other. Data processing has also reached new levels of sophistication. The amount of information being generated by these observations is staggering. Petabytes of data that require specialized algorithms and massive computing power to analyze. Machine learning systems are being used to identify patterns and anomalies that human observers might miss. Perhaps most impressively, all this technology is being coordinated across international boundaries and different institutions. Researchers from around the world are sharing data in real time, collaborating on analysis, and combining their expertise to understand what 3 Atlas is telling us. This technological dimension of the 3 Atlas investigation represents a triumph of human ingenuity and cooperation. It demonstrates how far we've come in our ability to observe and understand the cosmos, and it sets the stage for even more ambitious investigations of future interstellar visitors. As December approaches, these instruments will be working overtime, gathering as much data as possible during the optimal observation window. Whatever 3 Atlas ultimately proves to be, the technological capabilities we've developed to study it will benefit many areas of scientific research for years to come. The technology of detection reminds us that scientific progress depends not just on clever ideas, but also on the tools we build to test those ideas. By pushing the boundaries of observational capability, we expand the frontiers of knowledge and open new windows on the cosmos. Chapter 42. The Mathematics of Trajectory. Analysis. Let's dive into the mathematical wizardry that allows us to calculate 3 Atlas's path with such precision. This isn't just simple arithmetic, we're talking about complex calculations that account for the gravitational influence of multiple bodies, relativistic effects, and even the tiny push from gas jets erupting from the object's surface at its core. Trajectory analysis relies on Newton's laws of motion and gravitation, but with some important modifications for extreme precision. The basic principle is simple. Objects in space move along paths determined by the gravitational forces acting on them. But calculating those paths with the precision needed for 3 Atlas requires sophisticated mathematical techniques. One challenge is that 3 Atlas is influenced by multiple gravitational sources. The Sun's gravity is the dominant force, but Jupiter, Saturn, and even Earth exert measurable effects on the object's trajectory. Each of these influences must be calculated and combined to determine the overall path. This is where the unbody problem comes in, the challenge of calculating the motion of multiple objects interacting gravitationally. While there's no general analytical solution to this problem for 3 or more bodies, numerical methods can provide extremely accurate approximations. Researchers use what's called numerical integration to calculate 3 Atlas's trajectory. This involves breaking the object's path into tiny time steps and calculating the forces and resulting motion at each step. By making these steps small enough, the calculation can achieve remarkable precision. But it gets even more complicated. 3 Atlas is experiencing non-gravitational forces as well. The push from gas jets erupting from its surface as ice sublimate in sunlight. These forces are tiny compared to gravity, but they're measurable and must be accounted for in precise trajectory calculations. Relativistic effects also need to be considered, though they're small for 3 Atlas. General relativity predicts that massive objects curve space-time, affecting the motion of other objects nearby. For most solar system calculations, these effects are negligible, but for the precision needed to track 3 Atlas, they're included in the calculations. The mathematical models also need to account for the fact that we're observing 3 Atlas from Earth, which is itself moving around the Sun. This means we need to transform between different reference frames: the Earth's frame, the Sun's frame, and the object's frame, each with its own coordinate system and motion. What's particularly impressive is that researchers can calculate 3 atlases' trajectory not just forward in time but backward as well. By running these calculations in reverse, they can trace the object's path through interstellar space. Though the uncertainties grow the farther back they go, these mathematical calculations are verified through observations. Each new measurement of 3 atlases' position provides a data point that can be compared with the calculated trajectory. If there's a discrepancy, the models are refined to better match the observations. The precision of these calculations is remarkable. Researchers can predict 3 atlases' position months or even years in advance, with accuracy measured in kilometers or less across interplanetary distances. This precision is essential for planning observations and for detecting any deviations that might indicate artificial course corrections. The mathematics of trajectory analysis represents a beautiful intersection of physics, computation, and observational astronomy. It demonstrates how mathematical models can help us understand and predict the behavior of objects across vast distances of space and time. As December's observations approach, these trajectory calculations will become even more important. They'll help ensure that telescopes are pointed at exactly the right place at exactly the right time, maximizing the scientific return from the limited observation window. The mathematical dimension of the 3 Atlas investigation reminds us that behind the exciting discoveries and mysterious observations lies a foundation of rigorous calculation and analysis. It's through this mathematical work that we're able to translate raw observations into understanding of the object's behavior and origins. Chapter 43. The Chemistry of Interstellar Objects. The chemical composition of 3 Atlas provides some of the most compelling evidence that this object is unusual. Let's break down what we're seeing and why it matters. Using chemistry that would make your high school science teacher's head spin. First, the basics. Comets and asteroids contain various ethers, organic compounds, and minerals that reflect where and how they formed. By analyzing the light reflected and emitted by these objects, we can determine their chemical composition with remarkable precision. 3. Atlas is releasing a variety of gases as it approaches the Sun, and its surface ethers sublimate. Spectroscopic analysis has detected water, carbon dioxide, carbon monoxide, carbonyl sulfide, and cyanide, all compounds found in various solar system comets. So far, so normal. But here's where it gets weird. The object is releasing carbon dioxide at a rate roughly 8 times higher than water. Most comets are dominated by water ice, with carbon dioxide making up a smaller fraction of their composition. This inverted ratio suggests that 3 Atlas either formed in an extremely cold environment, where carbon dioxide ice is more stable, or it has an unusual surface composition. Even stranger is the detection of nickel tetracarbonyl, a compound with the formula nicarbon monoxide. For this is where chemists really start scratching their heads. Nickel tetracarbonyl has never been observed in nature, only in industrial manufacturing processes where it's used in nickel refining. The very large telescope detected nickel vapor being released at a rate of approximately 4.6 grams per second. Nickel emission from comets isn't unprecedented. Several solar system comets have shown it, and it was detected in the interstellar comet 2I Borisov. But what's unusual about 3 Atlas is the apparent absence of iron dot. In nearly every documented Comet, nickel and iron appear together in roughly equal proportions. This makes sense because nickel and iron form together in supernova explosions, travel together through interstellar space, and appear together in primitive solar system materials. Finding one without the other is like finding a lock without. A key not impossible, but suggesting unusual circumstances. Several explanations have been proposed for this nickel-iron discrepancy. Perhaps iron is present but not being detected due to specific conditions in the coma. Perhaps the iron is locked in compounds that don't break down as easily as the nickel-bearing materials. Perhaps observational limitations prevented detection, and the required sensitivity. Another chemical peculiarity is what scientists call carbon chain depletion. 3. Atlas shows unusually low levels of the 2-carbon and 3-carbon molecules that typically produce the green fluorescence, often seen in comets, yet astrophotographers have captured images showing 3 Atlas glowing distinctly green. Where did the green come from if the expected carbon chains were depleted? Possibly from cyanide, which the Very Large Telescope detected in increasing concentrations. Possibly from buried material finally being exposed as surface layers sublimate away. Possibly from chemical processes we don't fully understand occurring under the specific conditions this object experienced. Each of these chemical peculiarities has plausible, natural explanations. None individually requires invoking artificial construction, but collectively they paint a picture of an object whose composition doesn't quite match the typical profiles we've established from studying thousands of comets and asteroids in our own solar system. The chemistry of 3 Atlas also provides clues about its origin. The specific isotopic ratios of elements like carbon, hydrogen, and oxygen can help identify where in the galaxy the object might have formed. Different regions of the galaxy have different chemical signatures based on their star formation history. The detection of organic compounds is particularly interesting from an astrobiological perspective. While these compounds don't indicate life itself, they do suggest that the chemical building blocks of life might be common throughout the galaxy. 3 Atlas is essentially delivering samples of another star. Systems chemistry to our doorstep. As December's observations approach, researchers will be looking for any changes in the object's chemical composition. Will new compounds be revealed? As surface layers sublimate away, will the ratios of different gases change as the object moves away from the sun? Each chemical clue helps piece together the puzzle of what 3 Atlas is and where it came from. The chemical dimension of the 3 Atlas's investigation reminds us that the cosmos is not just empty space, but a rich chemical environment with diverse processes at work. By studying the chemistry of interstellar objects, we're learning about the chemical evolution of the galaxy and the distribution of the elements that make up planets and potentially life. Whatever 3 Atlas ultimately proves to be, it's unusual. Chemistry has already expanded our understanding of what's possible in interstellar space and challenged our assumptions about the composition of objects from other star systems. Chapter 44. The Physics of Interstellar Travel. Let's get real about what it would take to send an object like 3 Atlas across interstellar distances. The physics involved is mind-boggling, and understanding these challenges helps us appreciate why the object's characteristics are so unusual from an engineering perspective. First, the distances. Even the nearest star to our Sun, Proxima Centauri, is about 4.2 light years away. That's roughly 25 trillion miles. 3 Atlas is coming from much farther than that, likely from hundreds or even thousands of light years away. The energy required to cross such vast distances is astronomical. To put this in perspective, if 3 Atlas were traveling at the speed of the Voyager spacecraft, about 38,000 miles per hour, it would take more than 70,000 years to travel from Proxima Centauri to our solar system. Yet here it is, suggesting either a much higher velocity or a much longer travel time. The velocity of 3 Atlas relative to our Sun is about 67 kilometers per second roughly, 150,000 miles per hour. That's fast by human standards, but still slow enough that a journey from even a relatively nearby star would take tens of thousands of years. This timescale has important implications for how such a probe would need to be designed over such long time periods. The probe would need to withstand radiation, damage, micrometeoroid impacts, and the gradual degradation of materials. It would need power systems that could operate for millennia, navigation systems that could maintain course without external reference, and communication systems that could transmit across interstellar distances. One solution to these challenges is what's called a sleeper probe, a spacecraft that remains dormant for most of its journey, activating only when it approaches a target star system. This approach would conserve energy and reduce wear on systems, but it would require sophisticated autonomous systems to determine when and where to activate. The propulsion system presents another set of challenges. Conventional chemical rockets, like those we use for space missions today, simply don't have the specific impulse efficiency needed for practical interstellar travel. More advanced options might include nuclear propulsion, solar sails, or even more exotic technologies. Interestingly, the mass of 3 Atlas minus 33 billion tons actually makes sense from an interstellar travel perspective. A massive object would be more resistant to course changes from impacts or radiation pressure, making it more likely to maintain its trajectory over long time periods. The trajectory itself is remarkable from a physics perspective. 3 Atlas isn't just passing through our solar system randomly, it's on a path that brings it relatively close to multiple planets. This suggests either an incredible coincidence or careful trajectory planning that would require precise calculations and possibly course corrections. The physics of those potential course corrections is particularly interesting. Traditional rockets would require enormous amounts of propellant to change the trajectory of such a massive object. More efficient options might include gravitational assists using planetary gravity to alter course, or advanced propulsion systems like electromagnetic drives. The timing of the Perihelion passage during solar conjunction is also intriguing from a physics perspective. If the object made course corrections at perihelion, the Sun's gravity would amplify the effect of any thrust applied, a principle known as the Orbital effect. This would be an efficient way to adjust trajectory while minimizing fuel requirements. The thermal physics of 3 Atlas is another puzzle. The object is maintaining a relatively stable temperature despite varying distances from the Sun. This suggests either unusual thermal properties or active temperature regulation systems that would be characteristic of engineered technology rather than natural formation. The object's ability to survive perihelion passage, its closest approach to the Sun, is also noteworthy. Many comets break apart or fragment when they pass close to the Sun due to thermal stress and outgassing forces. The fact that 3 Atlas survived this passage intact suggests either robust structural integrity or protective systems that go beyond what we'd expect from a natural object. From a physics perspective, perhaps the most intriguing aspect of 3 Atlas is its apparent lack of non-gravitational acceleration despite significant outgassing. According to physics, the gas jets erupting from the surface should create thrust that alters the object's trajectory. The fact that we don't observe this suggests either the object is much more massive than calculated or the outgassing is somehow balanced or controlled. Each of these physical characteristics, the mass, trajectory, thermal properties, survival of perihelion, and lack of non-gravitational acceleration presents a puzzle from the perspective of conventional physics. While each might have a natural explanation, collectively they paint a picture of an object that seems optimized for long-distance interstellar travel. The physics of 3 Atlas reminds us that the universe operates according to consistent laws. But the ways these laws manifest can be surprising and complex. By studying this object, we're not just learning about a specific interstellar visitor, we're expanding our understanding of what's physically possible in the cosmos. As observations approach, physicists will be looking for any additional clues about the object's physical properties and behavior. Each new piece of information helps refine our understanding of how such an object could exist and what it might represent. The physics dimension of the 3 Atlas investigation bridges the gap between theoretical understanding and observational reality. It challenges us to apply physical principles to an object that pushes the boundaries of what we consider normal, potentially expanding our understanding of physics itself in the process. Chapter 45. The biology of interstellar objects. While it might seem strange to talk about biology in the context of an object that's likely just rock and ice, the investigation of 3 Atlas has important implications for astrobiology, the study of life in the universe. Let's explore how this interstellar visitor connects to questions about life beyond Earth. First, the concept of panspermia, the idea that life or its building blocks can be transported between planets or even between star systems. If 3 Atlas contains organic compounds, as spectroscopic analysis suggests, it represents a potential mechanism for distributing the chemical precursors of life throughout the galaxy. The detection of organic molecules in 3 Atlas is particularly significant from an astrobiological perspective. While these compounds don't indicate life itself, they do suggest that the chemical building blocks of life might be common throughout the galaxy. Each interstellar object that passes through our solar system is essentially delivering samples of another star system's chemistry to our doorstep. The survival of these organic compounds during interstellar travel is another interesting question. The object has been exposed to cosmic radiation for potentially millions of years. Understanding how organic molecules can survive such conditions helps us assess the likelihood that life's building blocks could be transported between star systems. The chemistry of 3 Atlas also provides clues about the conditions in its parent star system. The specific compounds and the ratios can tell us about the temperature, radiation environment, and chemical evolution of the region where the object formed. This information helps us understand the diversity of environments in the galaxy that might be conducive to life. From a biological perspective, perhaps the most intriguing aspect of 3 Atlas is the possibility that it could be intentionally designed to interact with life. If the object is artificial, it might contain instruments specifically designed to detect biosignatures, chemical or physical indicators of life. The trajectory of 3 Atlas, which brings it relatively close to Earth, might be significant. From an astrobiological perspective, if the object is a probe designed to study life, passing near a planet that clearly supports life would be a logical part of its mission. The close approach distance of 1.8 astronomical units might represent a balance between close enough to detect signs of life and far enough to avoid potential contamination or interference. The timing of the object's passage through our solar system is also interesting from an astrobiological perspective. Earth has been supporting life for billions of years, but only in the last few centuries has it shown clear signs of technological civilization. If 3 Atlas is designed to detect life, its arrival now could be either coincidental or purposeful. The investigation of 3 Atlas also helps us develop methods for detecting life on other worlds. The techniques used to analyze the object's composition could be applied to exoplanet, atmospheres, or other solar system bodies where life might exist. Each advance in our analytical capabilities brings us closer to answering the fundamental question of whether we're alone in the universe. Perhaps most importantly, 3 Atlas reminds us that the conditions necessary for life might not be unique to Earth. The object carries evidence of chemical processes occurring in other star systems, some of which might be similar to processes that led to life on Earth. This suggests that the universe might be filled with worlds where life could arise. Given the right conditions, as December's observations approach, astrobiologists will be particularly interested in any additional information about the object's organic content and whether it shows any signs of biological processes. While the probability is low, the discovery of clear biological evidence in 3 Atlas would revolutionize our understanding of life in the universe. The biological dimension of the 3 Atlas's investigation connects the study of interstellar objects to one of humanity's most fundamental questions. Are we alone? By exploring this possibility, we're not just learning about a specific object. We're expanding our perspective on life's potential distribution throughout the cosmos. Whatever 3 Atlas ultimately proves to be, its investigation has already advanced our understanding of the chemical conditions that exist throughout the galaxy and the potential for life to arise in diverse environments. Each interstellar object we study adds to our knowledge of the cosmic ingredients that might combine to form life elsewhere. Chapter 46. The Information Theory Perspective. Let's dive into a fascinating angle on 3 Atlas that you might not have considered: the information theory perspective. This approach looks at the object through the lens of information, content, complexity, and patterns, offering insights that complement traditional physical and chemical analyses. From an information theory standpoint, natural objects and artificial objects often differ in their information content. Natural processes tend to produce patterns with specific statistical properties, while intelligent design often creates patterns with different characteristics, more structure, less randomness, and more efficient encoding of information. One approach is to analyze the light curve of 3 Atlas, how its brightness changes over time. Natural objects typically show random variations in brightness based on rotation and surface features. Artificial objects might display more regular patterns or changes that don't fit natural statistical distributions. The object's spectral data can also be analyzed from an information theory perspective. Natural chemical processes produce specific patterns of spectral lines and intensities. Artificial processes might create different patterns, perhaps more efficient use of certain wavelengths or unusual combinations of elements that wouldn't occur through natural chemistry. The trajectory information provides another opportunity for information theory analysis. Natural orbital dynamics follow precise mathematical laws, but the specific path of 3 Atlas through our solar system might contain information if it's artificial. The sequence of planetary encounters, the timing of perihelion, and the precise approach distances could encode information if they're deliberately chosen rather than coincidental. Even the object's shape and surface features, when we can resolve them, can be analyzed from an information theory perspective. Natural objects tend to have certain statistical properties in their shape and surface texture. Artificial objects might show different characteristics, more symmetry, more efficient use of materials, or patterns that don't match natural formation. Processes. Information theory can also help us understand the communication potential of 3 Atlas. If the object is artificial, it might be designed to communicate information in various ways, through radio signals, light patterns, or even gravitational effects. Information theory provides tools for detecting and analyzing such communications, even if they're subtle or encoded in ways we don't immediately recognize. The concept of Kolmogorov complexity is particularly relevant here. This mathematical concept measures the complexity of an object based on the shortest possible description of it. Natural objects often have high Kolmogorov complexity. They require detailed descriptions because they contain random elements. Artificial objects might have lower complexity if they're efficiently designed, or they might have specific patterns of complexity that indicate intelligent design. Another information theory concept relevant to 3 Atlas is algorithmic probability. The likelihood that an object could be generated by a simple algorithm or process. Natural objects typically have high algorithmic probability because they're generated by relatively simple physical processes. Artificial objects might have lower algorithmic probability if they require complex design processes. Information theory can also help us understand the efficiency of 3 Atlas if it's artificial. Natural evolution often produces solutions that work but aren't necessarily optimal. Intelligent design might create more efficient solutions. For example, a shape that minimizes drag during interstellar travel, or a thermal regulation system that optimizes energy use. From a communication perspective, information theory helps us think about how an artificial probe might transmit information back to its creators. It might use efficient encoding methods, error-correcting codes, or transmission strategies that maximize the likelihood of successful communication across interstellar distances. The information theory perspective on 3 Atlas doesn't provide definitive answers about whether the object is natural or artificial, but it offers additional tools and frameworks for analysis. By looking at the object through the lens of information, content, and complexity, we might detect patterns that would be missed by traditional physical or chemical analysis. As December's observations approach, researchers with expertise in information theory will be analyzing the incoming data for any patterns that might indicate artificial origin. This complementary approach to the investigation adds another layer to our comprehensive analysis of 3 Atlas, the information theory dimension. Of the 3 Atlas, investigation reminds us that the universe contains not just matter and energy, but also information. By studying how information is structured, transmitted, and processed in cosmic objects, we gain new insights into the fundamental nature of reality and our place within it. Whatever 3 Atlas ultimately proves to be, the information theory perspective enriches our understanding of how to distinguish between natural and artificial phenomena and provides tools that will be valuable for future investigations of unusual cosmic objects. Chapter 47: The Sociology of Scientific Discovery. The investigation of 3 Atlas offers a fascinating case study in how scientific communities process and respond to potentially revolutionary discoveries. Let's explore the social dynamics at play and what they reveal about how science actually works in practice. One of the most striking aspects of the 3 Atlas investigation has been the diversity of responses within the scientific community. Some researchers have embraced the possibility of artificial origin as a legitimate hypothesis worth investigating, while others have been more skeptical, emphasizing natural explanations and caution about jumping to extraordinary conclusions. This diversity of perspectives reflects a healthy aspect of scientific discourse. Science progresses not through uniform agreement, but through the collision of different ideas, approaches, and interpretations. The debate surrounding 3 Atlas demonstrates how scientific communities self-correct and refine their understanding through critical discussion and evidence-based argumentation. The role of institutional authority in the 3 Atlas investigation is particularly interesting. Established scientific institutions have generally taken a cautious approach, emphasizing natural explanations and the need for extraordinary evidence before considering artificial origin. This institutional conservatism serves an important function. It prevents premature conclusions and maintains scientific credibility. At the same time, individual researchers and smaller research groups have been more willing to explore unconventional hypotheses. This dynamic between institutional caution and individual initiative creates a productive tension that allows science to explore bold ideas while maintaining rigorous standards of evidence. The publication patterns surrounding 3 Atlas also reveal interesting sociological dynamics. Papers discussing the object's unusual characteristics and potential artificial origin have appeared in various venues. From mainstream journals to preprint servers, the diversity of publication venues reflects different levels of acceptance within the scientific community and different approaches to peer review. The media's role in shaping the scientific discourse around 3 Atlas cannot be overlooked. Media coverage has influenced public perception of the investigation, which in turn affects funding priorities, institutional responses, and even how researchers approach their work. The relationship between scientific communities and media outlets is complex and mutually influential international dimensions of the 3 Atlas investigation reveal interesting sociological patterns as well. Researchers from different countries have sometimes taken different approaches to the object, reflecting cultural and institutional differences in how science is conducted and funded. These international variations enrich the investigation but also create challenges for coordination and consensus building. The sociology of expertise is another relevant dimension. Different kinds of experts, astronomers, physicists, chemists, engineers, and even philosophers have contributed different perspectives to the 3 Atlas investigation. The interaction between these different forms of expertise creates a more comprehensive understanding, but also involves complex social dynamics of authority, credibility, and interdisciplinary communication. The role of citizen scientists in the 3 Atlas investigation represents an interesting sociological development. Amateur astronomers and enthusiasts have contributed observations and analysis, challenging traditional boundaries between professional and amateur science. This democratization of scientific participation reflects broader changes in how knowledge is produced and validated. The funding patterns surrounding 3 Atlas also reveal sociological dimensions. Research priorities and funding decisions reflect not just scientific merit but also social values, political considerations, and institutional priorities. The investigation of 3 Atlas has benefited from some dedicated funding but has also competed with other research priorities for limited resources. The sociology of scientific consensus is particularly relevant to 3 Atlas. How does a scientific community reach consensus on a question as extraordinary as whether an object might be artificial? The process involves not just evaluation of evidence, but also social negotiation, authority dynamics, and the gradual building of agreement through publication, discussion, and further research. As December's observations approach, the sociological dynamics of the 3 Atlases investigation will become even more prominent. Whatever the observations reveal, the scientific community will need to process and interpret the results through these complex social dynamics. The sociology of scientific discovery surrounding 3 Atlas reminds us that science is not just a dispassionate search for truth, but a human activity embedded in social contexts. By understanding these social dimensions, we gain insight into how scientific knowledge is produced, validated, and integrated into our broader understanding of the world. Whatever 3 Atlas ultimately proves to be, the investigation has already provided valuable insights into how scientific communities process potentially revolutionary discoveries and how the social dynamics of science shape our understanding of the cosmos. Chapter 48. The Psychology of Belief and Skepticism. The investigation of 3 Atlas has triggered a wide range of psychological responses, from eager acceptance of artificial origin theories to stubborn insistence on natural explanations. Let's explore the psychological factors that influence how people process and interpret the evidence surrounding this mysterious object. One of the most prominent psychological factors at play is confirmation bias, our tendency to interpret new information in ways that confirm our existing beliefs. People who already believe in extraterrestrial intelligence are more likely to see 3 Atlas as potential evidence of that belief, while skeptics are more likely to interpret the same data as supporting natural explanations. This confirmation bias is reinforced by what psychologists call the availability heuristic, our tendency to judge the likelihood of events based on how easily examples come to mind. People who have consumed science fiction about alien visitors might find the idea of an artificial 3 atlas more plausible than those who haven't been exposed to such narratives. The concept of cognitive dissonance is also relevant here. When faced with evidence that challenges our deeply held beliefs, we experience psychological discomfort. To reduce this discomfort, we might either reject the evidence or modify our beliefs. The investigation of 3 atlas creates cognitive dissonance for people on both sides of the debate. The psychology of pattern recognition plays a crucial role as well. Humans have evolved to see patterns even in random data, a tendency that served our ancestors well when identifying predators or finding food sources that can lead us to see significance where none exists. The unusual characteristics of 3 atlas provide fertile ground for pattern recognition, both accurate and illusory. The authority bias also influences how people interpret information about 3 atlas. We tend to give more weight to the opinions of experts or authority figures, even when their expertise might not be directly relevant to the question at hand. This can lead to over-reliance on certain voices in the debate and underappreciation of others. The psychology of uncertainty tolerance is another relevant factor. Some people are comfortable with ambiguity and uncertainty, while others find it deeply unsettling. Those with low uncertainty tolerance might be more inclined to reach firm conclusions about 3 atlas one way or another, while those more comfortable with uncertainty might be content to suspend judgment until more evidence is available. The concept of motivated reasoning is particularly relevant to 3 atlas. This refers to our tendency to process information in ways that serve our goals or motivations. For some, the goal might be to maintain a particular worldview. For others, to be seen as open-minded, and for still others to demonstrate scientific rigor. These motivations influence how we interpret the evidence. The psychology of belief perseverance also plays a role. Once we've formed a belief about 3 atlas, we tend to hold on to that belief even when presented with contradictory evidence. This helps explain why opinions about the object can be so resistant to change, even as new data emerges. The social identity theory of psychology is relevant as well. Our beliefs about 3 atlas can become part of our identity, connecting us with certain groups and distinguishing us from others. This social dimension can make us more resistant to changing our beliefs, as doing so might mean changing our social affiliations. The psychology of awe and wonder also influences how people respond to 3 atlas. The possibility that we might be observing evidence of extraterrestrial technology triggers profound emotional responses that can overshadow rational analysis. This emotional dimension is part of what makes the object so compelling, but can also cloud judgment. As observations approach, these psychological factors will become even more prominent. Whatever the observations reveal, people will interpret the results through these psychological filters, often reaching very different conclusions based on the same evidence. The psychology of belief and skepticism surrounding 3 atlas reminds us that scientific understanding is not just about objective evidence, but also about how human minds process that evidence. By understanding these psychological factors, we can become more aware of our own biases and more open to considering evidence that challenges our preconceptions. Whatever 3 Atlas ultimately proves to be, the investigation has already provided valuable insights into human psychology and how we process potentially revolutionary discoveries about our place in the cosmos. Chapter 49. The Ethics of Investigation and Communication. The investigation of 3 Atlas raises important ethical questions that go beyond the scientific details of the object itself. Let's explore the ethical dimensions of how we study this mysterious visitor and how we communicate our findings to the public. One of the primary ethical considerations is how to allocate limited research resources, the telescopes and instruments being used to study 3 Atlas could also be used for other scientific investigations. There's an ethical question about how to balance the potential significance of studying 3 Atlas against other research priorities that might have more immediate practical benefits. The ethics of communication is another crucial dimension. How should researchers communicate their findings about 3 Atlas, especially when the evidence is ambiguous? There's a tension between the scientific value of openness and the potential for premature speculation to mislead the public or create unnecessary anxiety. The question of when to communicate findings is ethically complex as well. Should researchers wait until they have definitive conclusions before sharing results? Or should they communicate their progress even when uncertainties remain? Each approach has different ethical implications for scientific transparency and public understanding. The ethics of speculation is particularly relevant to 3 Atlas. Researchers have an ethical obligation to distinguish between what the evidence actually shows and what it might suggest. Speculation has value in exploring possibilities, but it needs to be clearly labeled as such to avoid misleading people about the strength of the evidence. The question of who gets to participate in the investigation raises ethical issues as well. Access to major telescopes and research funding is limited, creating questions about inclusion and equity in the scientific process. How can we ensure that diverse perspectives are represented in the investigation of 3 Atlas? The ethics of international cooperation is another important consideration. 3 Atlas is a global phenomenon, but research, resources, and capabilities are unevenly distributed around the world. There's an ethical question about how to ensure that the benefits of the investigation are shared globally and that all countries have the opportunity to contribute. The ethics of data sharing is particularly relevant to 3 Atlas. The data being collected has potential value beyond the immediate investigation. But there are questions about who should have access to it, under what conditions, and how it should be preserved for future research. The question of potential communication with an artificial 3 Atlas raises profound ethical issues. If the object were confirmed to be artificial, would we have an ethical obligation to attempt communication? What would be the appropriate content of such communication? Who would be authorized to speak for humanity? The ethics of preparation is another important dimension. If there's even a small possibility that 3 Atlas is artificial, do we have an ethical obligation to prepare for that possibility? This preparation might involve developing protocols for response, considering the implications for various aspects of society, and planning for different scenarios. The ethics of public engagement is also relevant. How should researchers engage with the public about 3 Atlas? There's a balance between maintaining scientific rigor and making the investigation accessible and interesting to non-experts. This balance has ethical implications for scientific literacy and public trust in science. The question of long-term implications raises ethical considerations as well. Whatever we learn about 3 Atlas could have profound implications for humanity's self-understanding and future development. Researchers have an ethical responsibility to consider these implications and to communicate them thoughtfully. As December's observations approach, these ethical dimensions will become even more prominent. The decisions researchers make about how to conduct the investigation and communicate their findings will have implications that extend far beyond the scientific details of the object itself. The ethics of investigating and communicating about 3 Atlas reminds us that scientific research doesn't exist in a moral vacuum. The choices researchers make about how to study this mysterious visitor and share their findings reflect values and priorities that have implications for how science serves society. Whatever 3 Atlas ultimately proves to be, the investigation has already highlighted important ethical questions that will be relevant to future scientific discoveries, with potentially profound implications for humanity's understanding of our place in the cosmos. Chapter 50. The philosophical implications of cosmic loneliness. The investigation of 3 Atlas forces us to confront a profound philosophical question. What would it mean if we discovered that we're not alone in the universe? This question strikes at the heart of how we understand ourselves, our significance, and our place in the cosmic order. The philosophical implications of discovering extraterrestrial technology would be revolutionary. For millennia, humanity has grappled with questions of cosmic significance. Are we special, unique, or merely one among many possible forms of life and intelligence? 3 Atlas represents a potential answer to this fundamental question. If 3 Atlas were confirmed as artificial, it would suggest that intelligence and technology are not unique to Earth. This would have profound implications for how we understand ourselves. It would suggest that the universe is likely filled with diverse forms of intelligence, each with its own perspective on reality and its own understanding of cosmic significance. The philosophical concept of anthropocentrism, the tendency to view human existence as central to the universe, would be challenged by confirmation of extraterrestrial technology. We would need to reconsider our place in the cosmic hierarchy and perhaps adopt a more humble view of our significance. The question of cosmic purpose would also be affected. If intelligence exists elsewhere, what does this suggest about the purpose or meaning of the universe? Does the widespread existence of intelligence suggest that the universe has some inherent tendency toward complexity and awareness? The philosophical implications for religion would be profound as well. Many religious traditions have grappled with the question of life beyond Earth, but actual evidence of extraterrestrial technology would force these traditions to confront new theological questions about the relationship between the divine and multiple forms of intelligent life. The concept of human uniqueness would be called into question as well. Throughout history, many philosophical and religious traditions have emphasized the special nature of human consciousness and intelligence. Discovery of extraterrestrial technology would challenge this assumption and force us to reconsider what makes human existence meaningful. The philosophical implications for ethics would be significant too. If we're not alone in the universe, we might need to develop ethical frameworks that consider not just human interests, but potentially the interests of other intelligent beings as well. This could transform our understanding of moral responsibility. An ethical consideration, the question of knowledge itself, would be affected philosophically. If we discovered evidence of extraterrestrial intelligence, it would suggest that there are other ways of knowing and understanding the universe beyond human cognition. This could challenge our philosophical assumptions about the nature and limits of knowledge. The concept of cosmic loneliness would be transformed as well. Humanity has long grappled with the question of whether we're alone in the universe. Confirmation that we're not would alleviate this existential loneliness, but might introduce new philosophical questions about our relationship to other intelligent beings. The philosophical implications for human destiny would be profound as well. If the universe is filled with intelligent life, what does this suggest about humanity's future? Are we part of a larger cosmic community of intelligent beings, each with its own destiny and purpose? The question of cosmic meaning would be affected as well. If intelligence exists throughout the universe, does this suggest that the universe has inherent meaning or purpose? Or are we still left with the philosophical challenge of creating meaning in a potentially indifferent cosmos? As December's observations approach, these philosophical questions become more immediate. Whatever the observations reveal, we'll need to grapple with the philosophical implications of what we learn about 3 Atlas, and what it suggests about our place in the cosmos. The philosophical dimension of the 3 Atlas investigation reminds us that scientific discoveries don't exist in isolation from our broader understanding of meaning, purpose, and significance. By contemplating these philosophical questions, we enrich our appreciation of why the investigation matters, and what it might reveal about the nature of existence itself. Whatever 3 Atlas ultimately proves to be, the investigation has already prompted important philosophical reflections that help us clarify our values, beliefs, and assumptions about our place in the cosmos. These philosophical dimensions will continue to inform our understanding of the object and its implications, regardless of what December's observations reveal. Chapter 51: The Future of Interstellar Object Research. Regardless of what 3 Atlas ultimately proves to be, its appearance has already transformed how we approach the study of interstellar objects. Let's explore how this investigation is shaping the future of this field and what we can expect in the years to come. One of the most significant developments has been the establishment of more systematic approaches to detecting and tracking interstellar objects. The Vera C. Rubin Observatory, fully operational as of 2025, surveys the entire visible sky every few nights and is dramatically increasing our ability to detect these visitors as they pass through our solar system. The investigation of 3 Atlas has also highlighted the need for dedicated instruments specifically designed to study interstellar objects. Researchers are proposing telescope arrays and space-based observatories, optimized for detecting and characterizing these objects. As they approach our solar system, international coordination has improved significantly as well. The 3 Atlas investigation has demonstrated the value of global cooperation in studying these objects, leading to more formal agreements about data sharing, observation, coordination, and collaborative analysis. The development of rapid response protocols represents another important advance. Interstellar objects move quickly through our solar system, leaving limited time for observation. The 3 Atlas experience has highlighted the need for protocols that can mobilize observational resources quickly when a new object is detected. Citizen science has become increasingly important in interstellar object research. The investigation of 3 Atlas has demonstrated how amateur astronomers and enthusiasts can contribute valuable observations and analysis, leading to more formal integration of citizen science into research programs. Theoretical modeling of interstellar objects has advanced significantly as well. The unusual characteristics of 3 Atlas have prompted researchers to refine their models of how these objects form, evolve, and behave during their passage through our solar system. The development of specialized analytical techniques represents another important advance. The investigation of 3 Atlas has required new approaches to data analysis, particularly for detecting subtle anomalies that might indicate artificial origin. These techniques will be valuable for studying future interstellar objects. Mission concepts for intercepting future interstellar objects have gained traction as well. While we don't currently have the capability to rendezvous with an object like 3 Atlas, the investigation has inspired more serious consideration of missions that could physically study these visitors up close. The establishment of formal frameworks for evaluating potential technosignatures is another important development. The 3 Atlas investigation has highlighted the need for systematic approaches to distinguishing between natural and artificial characteristics, leading to more formal methodologies for this evaluation. Public engagement with interstellar object research has increased significantly as well. The mystery surrounding 3 Atlas has captured public imagination, leading to greater support for research funding and more opportunities for educational outreach. The integration of diverse disciplinary perspectives represents another important advance. The investigation of 3 Atlas has demonstrated the value of bringing together experts from astronomy, physics, chemistry, engineering, philosophy, and other fields to address complex questions about these objects. As we look to the future, we can expect to detect many more interstellar objects as our observational capabilities improve. Each new visitor will provide additional data points that help us understand the diversity of these objects and their implications for our understanding of the cosmos. The future of interstellar objects research will likely involve more sophisticated detection methods, more comprehensive observation strategies, and more advanced analytical techniques. We'll develop better models of how these objects form and evolve, and will refine our ability to distinguish between natural and artificial characteristics. Perhaps most importantly, the investigation of 3 Atlas has established a template for how to approach future interstellar objects that display unusual characteristics. The methodological, institutional, and conceptual frameworks developed during this investigation will inform how we study future visitors to our solar system. The future of interstellar object research reminds us that scientific understanding advances not just through individual discoveries, but through the development of better methods, instruments, and conceptual frameworks for investigation. By improving our ability to study these cosmic visitors, we expand our knowledge of the galaxy and our place within it. Whatever 3 Atlas ultimately proves to be, its investigation has already transformed how we approach the study of interstellar objects and set the stage for exciting discoveries in the years to come. Chapter 52. The Legacy of 3 Atlas. Regardless of what December's observations reveal, 3 Atlas has already secured its place in the history of astronomical investigation. Let's explore the legacy this mysterious visitor will leave behind, and how it will influence our understanding of the cosmos for years to come. One of the most significant aspects of 3 Atlas's legacy is how it has transformed our approach to studying interstellar objects. Before its arrival, these visitors were treated as curiosities, interesting but not particularly revolutionary. 3 Atlas has elevated interstellar objects to a new level of scientific and public interest. The methodological innovations developed during the 3 Atlas investigation represent another important part of its legacy. The new analytical techniques, observational strategies, and collaborative approaches developed to study this object will benefit many areas of astronomical research for years to come. The conceptual frameworks established for evaluating potential technosignatures will also be part of 3 Atlas's legacy. The investigation has prompted more serious consideration of how to distinguish between natural and artificial characteristics, leading to more systematic approaches to this question. The public engagement inspired by 3 Atlas represents another significant aspect of its legacy. The mystery surrounding this object has captured public imagination in a way few astronomical phenomena have, leading to increased interest in space science and more support for research funding. The international cooperation demonstrated during the 3 Atlas investigation will also be part of its legacy. The collaboration between researchers from around the world to study this object provides a model for how global scientific cooperation can work even in a politically divided world. The educational opportunities created by 3 Atlas represent another important legacy. The object has inspired countless students to pursue careers in science and technology, and it has provided educators with a compelling case study for teaching about the scientific method and cosmic exploration. The philosophical reflections prompted by 3 Atlas would also be part of its legacy. The investigation has forced us to confront fundamental questions about our place in the cosmos and the possibility of life beyond Earth, enriching our understanding of these profound issues. The technological innovations spurred by the 3 Atlas investigation represent another significant aspect of its legacy. The new instruments, data analysis methods, and communication platforms developed to study this object will have applications far beyond interstellar object research. The cultural impact of 3 Atlas will also be part of its legacy. The object has inspired art, literature, music, and other forms of creative expression that reflect our enduring fascination with the cosmos and our place within it. The policy discussions prompted by 3 Atlas will be another important part of its legacy. The investigation has highlighted the need for better frameworks for responding to potentially revolutionary discoveries, leading to more serious consideration of how to prepare for such possibilities. Whatever December's observations reveal, 3 Atlas has already earned its place in the history of human exploration of the cosmos. It has challenged our assumptions, expanded our methodological capabilities, and inspired us to ask bigger questions about our place in the universe. The legacy of 3. Atlas reminds us that scientific investigations are not just about the specific objects or phenomena being studied, but about how they transform our understanding, our capabilities, and our relationship to the cosmos. By pushing the boundaries of knowledge and imagination, 3 Atlas has already secured its place as a significant chapter in humanity's ongoing cosmic exploration. As we await December's observations, we can appreciate that whatever the results, 3 Atlas has already made valuable contributions to science, education, and our collective understanding of the universe. These contributions will endure long after the object has left our solar system, continuing to inspire and inform future generations of cosmic explorers. The true legacy of 3 Atlas will be written not just in the scientific papers about its characteristics, but in the broader impact it has had on how we approach cosmic mysteries, how we collaborate across boundaries, and how we imagine our place among the stars.